the universe has always fascinated humanity, a vast and silent tapestry woven with unanswered mysteries. Yet, beyond the familiar cosmos of stars and galaxies, there may be more. Hidden dimensions, parallel realities, and entire worlds could exist just beyond the veil of our perception. The laws of physics as we know them might only be a local chapter in a much grander, more complex cosmic story. A design that stretches far beyond the confines of a single universe. It is this tantalizing possibility, this deep and enduring quest to understand the ultimate nature of reality, that has led humanity to build one of the most powerful and ambitious machines ever created, the Large Hadron Collider. This is not just an instrument of science. It is a time machine, a reality probe, a technological marvel designed to recreate the fiery, primordial conditions of the Big Bang and to unlock the deepest secrets of existence itself. Today, we embark on a journey into the heart of this scientific cathedral, an exploration that will take us from the colossal 27-kilometer ring buried deep beneath the Swiss-French border to the strange and beautiful realm of quantum collisions, where new and exotic forms of reality are forged for a fleeting, infinitesimal moment. We will explore the mind-bending concept of extra dimensions, the mysterious gravitational whispers of dark matter, and the ultimate philosophical challenge of a potential multiverse. Following the trail of the brilliant physicists and theorists who have dedicated their lives to this quest, we will examine the incredible discoveries that have already been made, and the profound, and often unsettling, questions that still haunt the frontiers of our knowledge. Could our reality be just one of a vast and perhaps infinite number of other realities? Are there other parallel versions of ourselves, living out the consequences of every choice we never made? And will the Large Hadron Collider, in its relentless and powerful probing of the subatomic world, finally provide us with the first tantalizing hints of an answer? The search for the ultimate truth has begun, and it is a search that is taking place not in the distant heavens, but in the deep, dark, and wonderfully mysterious heart of matter itself. The Large Hadron Collider, or LHC, stands as a monument to human curiosity and collaboration. Nestled at CERN, the European Organization for Nuclear Research, and straddling the border between Switzerland and France, this immense machine is a 27-kilometer-long underground circular tunnel, a racetrack for the very building blocks of our universe. Its purpose is both elegantly simple and profoundly ambitious: to accelerate subatomic particles, like protons, to speeds just shy of the speed of light, and then to smash them together with an energy that has not been seen in the cosmos since the first fiery moments after the Big Bang. In the subatomic debris of these cataclysmic collisions, scientists search for the ghostly signatures of new particles, new forces, and new symmetries of nature, seeking clues to the deepest mysteries of our existence. The LHC is the culmination of a long scientific lineage, the latest and most powerful in a series of particle accelerators that have, over the last century, peeled back the layers of reality, revealing an ever deeper and ever stranger subatomic world. But the LHC was designed with a specific set of profound and long-standing questions in mind, questions that had brought the field of particle physics to a critical juncture. Physicists were grappling with the origin of mass. Why do some fundamental particles possess it, while others do not? They were hunting for the identity of dark matter, the invisible substance that makes up the vast majority of the matter in the universe, and they were trying to understand the deep and seemingly miraculous asymmetry between matter and antimatter, the reason our universe is made of stuff at all. The standard model of particle physics, the remarkably successful theory that describes all the known fundamental particles and their interactions, provides a beautiful and coherent framework for our understanding of the subatomic world. But it is an incomplete story, It has glaring omissions. It does not include the force of gravity. It has no explanation for dark matter or dark energy. It cannot account for the matter-antimatter imbalance. The LHC was conceived as a standard model breaking machine, a powerful tool designed to find the cracks in our current understanding, the subtle anomalies that would point the way to a new, deeper, and more comprehensive theory of reality. The dream of a collider powerful enough to recreate the conditions of the early universe had been cherished by physicists for decades, but the technological hurdles were immense. It required the development of some of the most powerful superconducting magnets ever built, capable of generating magnetic fields thousands of times stronger than the Earth's, to bend the high-energy proton beams around the 27-kilometer ring. It required an ultra-high vacuum, emptier than interplanetary space, to ensure the proton beams could travel unimpeded on their journey. And it required the construction of some of the largest and most complex scientific instruments ever conceived, the massive cathedral-sized detectors like ATLAS and CMS that are designed to capture and to analyze the fleeting subatomic shrapnel of the particle collisions. After years of meticulous planning and a truly global collaborative construction effort involving thousands of scientists and engineers from over 100 countries, the LHC was finally completed and switched on in 2008. At its core, the science of the LHC is a form of cosmic archaeology. By smashing protons together with incredible energy, physicists are, for a fleeting, infinitesimal moment, recreating the hot, dense, and energetic conditions of the primordial universe. In that fraction of a second, new and exotic particles, some of which have not existed in nature since the Big Bang, can be forged from the pure energy of the collision, as described by Einstein's famous equation, E equals mc squared. Many of these particles are incredibly unstable, decaying into more familiar particles in a fraction of a second. The job of the giant detectors is to act as a kind of high-tech, three-dimensional digital camera, to track the paths, the energies, and the identities of the hundreds of particles that fly out from each collision, and to reconstruct the story of what happened in that moment of creation. It is a process of sifting through a mind-boggling amount of data, trillions of collisions every second, to search for the rare, telltale signature of a new particle, a new force, a new discovery. It is a search for a needle in a cosmic haystack, a search that is pushing the limits of our technology, our computational power, and our very understanding of the fundamental nature of reality. The immense energy of the particle collisions at the LHC is the key to its scientific power. In the world of particle physics, higher energy translates directly to the ability to probe smaller distances and to create heavier, more exotic particles. The journey of a proton at the LHC is a journey of almost unimaginable acceleration. It begins in a simple bottle of hydrogen gas. The hydrogen atoms are ionized, stripped of their single electron, leaving bare protons. These protons are then injected into a series of smaller pre-accelerator rings, where they are given a kick of energy by powerful oscillating electric fields in radio frequency cavities. With each kick, they move faster, and their path is guided and focused by a complex array of magnets. As they gain speed, they are passed from one accelerator to the next, like runners in a relay race, until they are finally injected into the main 27-kilometer ring. Here, they will circle for hours, making over 11,000 laps every single second, their energy boosted with each turn by the powerful superconducting radio frequency cavities. The protons travel in two counter-rotating beams, each beam containing trillions of protons, all traveling at an incredible 99.9999991% of the speed of light. At this extreme relativistic speed, each proton has the kinetic energy of a flying mosquito, a seemingly tiny amount of energy, but an immense amount when concentrated into a single subatomic particle, At 4 specific points around the ring, these 2 hair-thin beams of high-energy protons are focused down to an even smaller size and are made to cross through each other. This is where the scientific magic happens. In the vast majority of cases, the protons in the 2 beams will simply pass by each other without interacting. But occasionally, 2 protons will collide head-on, releasing their immense, concentrated energy in a tiny subatomic fireball, a miniature Big Bang. It is in this fireball, for a fleeting, infinitesimal moment, that the conditions of the early universe are recreated. The raw energy of the collision is converted into a shower of new particles, a fleeting glimpse of the exotic zoo of particles that populated the cosmos in its first moments. And surrounding these collision points are the giant general-purpose detectors, ATLAS and CMS. These are marvels of modern engineering, multi-story structures packed with layers of different kinds of sensors, each designed to detect a different type of particle. The inner layers, closest to the collision, are silicon pixel and strip detectors designed to track the paths of charged particles with incredible precision. Surrounding these are the calorimeters, which are designed to measure the energy of the particles by absorbing them. And on the outermost layers are the muon chambers, which are designed to detect muons, a heavier cousin of the electron, which are one of the few particles that can punch through all the inner layers of the detector. The amount of data generated by these detectors is staggering. Each collision can produce thousands of particles, and there are billions of collisions happening every second. It is a torrent of information that is far beyond the capacity of any human to analyze. And so, a complex, multi-layered trigger system is used to filter the data in real time, selecting only the most interesting and potentially significant events to be saved for later analysis. This is a process that relies on sophisticated and increasingly AI-driven algorithms to search for the specific telltale signatures of new physics. The reason the LHC requires such high energies is not just to create new particles, but also to test the predictions of our current theories in a new and unexplored regime. The standard model of particle physics has been remarkably successful, but it is an incomplete theory. By pushing to higher and higher energies, physicists are hoping to find the limits of the standard model, to find a place where its predictions break down, a place that will point the way to a new, more fundamental theory of reality. The LHC is not just a machine for discovering new particles. It is a machine for discovering new questions, for pushing the boundaries of our knowledge, and for revealing the deep and often hidden structure of the universe itself. One of the most profound and long-sought answers that the LHC was built to provide was the confirmation of the existence of the Higgs boson. This elusive particle, first theorized in the 1960s by a group of physicists including Peter Higgs, was the missing cornerstone of the standard model of particle physics. It was the key to understanding one of the most fundamental and yet most mysterious properties of our universe: the origin of mass. The standard model, in its original and most elegant form, predicted that all the fundamental particles should be massless. But this is clearly not the case. We know that electrons, quarks, and the W and Z bosons all have mass. The Higgs mechanism was the brilliant theoretical solution to this puzzle. It proposed the existence of a new invisible energy field that permeates all of space, now known as the Higgs field. In the very early hot universe, this field was off and all the particles were massless. But as the universe cooled, the Higgs field underwent a phase transition and turned on, acquiring a non-zero value everywhere in the vacuum. And it is the interaction of the other fundamental particles with this background Higgs field that gives them their mass. Imagine moving through a thick, viscous liquid like molasses. A particle that interacts strongly with the Higgs field is like a person trying to wade through this molasses. It experiences a drag, an inertia, which we perceive as mass. A particle that interacts weakly with the field experiences less drag and has a smaller mass. And a particle that does not interact with the field at all, like the photon, experiences no drag and remains massless. The Higgs boson is the quantum particle associated with this field. It is a localized, vibrating excitation of the Higgs field itself, a ripple in the cosmic molasses. The Standard Model made a precise prediction for the properties of the Higgs boson, but it did not predict its mass. Finding the Higgs and measuring its mass was one of the primary goals of the LHC. The task was not an easy one. The Higgs boson is incredibly unstable, decaying into other more familiar particles in an almost instantaneous fraction of a second. It is also incredibly rare, produced in only about 1 in every 10 billion proton-proton collisions at the LHC. The challenge for the experimentalists was to sift through the immense, chaotic debris of the collisions and to find the tiny, statistical excess of events that would signal the fleeting existence of the Higgs. It was a search that required the analysis of a truly astronomical amount of data, a task that pushed the limits of modern computing and statistical analysis. And then, on the 4th of July, 2012, in a historic and emotional announcement at CERN, the ATLAS and CMS collaborations jointly announced that they had, independently, discovered a new particle with a mass of about 125 gigaelectron volts, a particle whose properties were consistent with those of the long-sought Higgs boson. It was a moment of profound triumph for science, a confirmation of a 50-year-old theoretical prediction, and the culmination of one of the greatest and most ambitious scientific endeavors in human history. The discovery of the Higgs boson was a monumental achievement. It confirmed the existence of the Higgs field and provided the missing piece of the Standard Model puzzle. It gave us a deep and experimentally verified understanding of the origin of mass, one of the most fundamental properties of our reality. But in science, every answer seems to give rise to new and often deeper questions. And the discovery of the Higgs boson was no exception. While the particle's existence confirmed the general picture of the Higgs mechanism, its specific, measured properties have raised a host of new puzzles and have pointed the way towards a new and largely unexplored frontier of physics. For example, why is the mass of the Higgs boson so light? Quantum mechanics predicts that the Higgs mass should receive huge quantum corrections from its interaction with the virtual particles of the vacuum, which should drive its mass up to the Planck scale, the fundamental scale of quantum gravity, which is about 16 orders of magnitude heavier than what we observe. This hierarchy problem suggests that there must be some new physics, some new symmetry of nature, like supersymmetry. That is protecting the Higgs mass from these huge quantum corrections, but so far, the LHC has found no evidence for this new physics. Another profound mystery is the nature of the Higgs field's potential energy. The shape of this potential is what determines the stability of our universe's vacuum and the measured mass of the Higgs boson. When combined with the mass of the heaviest known particle, the top quark, suggests that our universe may not be in a truly stable, lowest energy state. It may be in a metastable, or false vacuum state, a state that is stable for now, but could one day, through a process of quantum tunneling, decay into a new, true vacuum state, an event that would rewrite the laws of physics and annihilate our entire cosmos in an instant. The Higgs boson, the very particle that gives our universe its substance, may also be the harbinger of its ultimate doom. Since 2012, the research at the LHC has shifted from a search for the Higgs to a detailed, precision study of its properties. By measuring its interactions with all the other known particles, and by searching for its potential interactions with new, as yet undiscovered, particles, physicists are hoping to use the Higgs boson as a portal, a window into the new physics that we know must lie beyond the standard model. The Higgs is not the end of the story. It is the beginning of a new chapter. A chapter that may lead us to a deeper understanding of dark matter, of quantum gravity, and of the ultimate fate of our universe. Despite the monumental success of the standard model and the triumphant discovery of the Higgs boson, the universe continues to present us with a host of deep and profound mysteries that lie beyond the reach of our current theories. The LHC, while confirming the last piece of the standard model puzzle, has, so far, failed to find any direct evidence for the new physics that we know must be there. This has led to a period of deep reflection and also of great excitement. In the world of particle physics, we are standing at a crossroads, a moment where the old, familiar map of reality has run out, and we are venturing into a truly uncharted territory. One of the most glaring and most humbling of these unsolved mysteries is the nature of dark matter. Our observations of the cosmos, from the rotation speeds of galaxies to the gravitational lensing of distant light, have provided overwhelming and incontrovertible evidence that the visible matter of our universe, the stars, the gas, the dust, is just the tip of a vast cosmic iceberg. About 85% of the matter in the universe is made of a mysterious, invisible substance that does not interact with light. It is dark. We know it is there because we can feel its gravitational pull, but we have no idea what it is. The standard model of particle physics has no place for dark matter. None of the known particles have the right properties to be the dark matter. This means that the vast majority of the matter in the universe is made of something new, something completely outside of our current and otherwise incredibly successful theory of reality. For decades, the leading candidate for the dark matter particle was the weakly interacting massive particle, or WIMP. This was a hypothetical particle, predicted by theories like supersymmetry, that would be heavy and would interact only through the weak nuclear force and gravity. This was an attractive idea, because a WIMP with the right mass and interaction strength would have been produced in just the right abundance in the early universe to account for the observed amount of dark matter today. This WIMP miracle, as it was called, made it the focus of an intense and multi-pronged experimental search. But after decades of searching in deep underground laboratories with satellite-based telescopes and at the Large Hadron Collider, we have found no definitive evidence for WIMPs. The parameter space for the simplest and most natural WIMP models has been almost completely ruled out. This has led to a WIMPless era in particle physics, a time of great creativity and of a renewed search for alternative dark matter candidates. Perhaps dark matter is made of actions, a hypothetical ultralight particle that was originally proposed to solve a different puzzle in the theory of the strong nuclear force. Or perhaps it is made of sterile neutrinos, a heavier and even more elusive cousin of the known neutrinos. Or perhaps it is part of a whole, hidden, dark sector of particles and forces that interacts with our own visible world only through very weak or portal interactions. Another profound and equally challenging mystery is the nature of antimatter. According to the laws of physics, the Big Bang should have produced matter and antimatter in almost perfectly equal amounts. But when a particle of matter meets its antimatter counterpart, they annihilate each other in a flash of pure energy. If the early universe had been perfectly symmetric, all the matter and antimatter would have been destroyed, leaving behind a cold, empty universe filled with nothing but photons. The very fact that we exist, that the universe is filled with galaxies, stars, and planets made of matter, is a testament to a deep and as yet unexplained asymmetry in the laws of nature. In the first moments of the universe, for some reason, a tiny excess of matter was created about one extra particle of matter for every billion particle-antiparticle pairs. All the substance of our universe is the leftover remnant of this primordial symmetry-breaking event. The Standard Model does contain a small amount of CP violation, a subtle difference in the way matter and antimatter behave. But it is far too small to account for the observed dominance of matter in the cosmos. There must be a new source of CP violation, a new physics beyond the Standard Model, that is responsible for our very existence. The LHC is searching for this new physics by studying the decays of certain rare particles, like B-mesons, with incredible precision, looking for any tiny deviation from the predictions of the Standard Model that could signal a new asymmetric interaction. And then there is the ultimate challenge, the holy grail of modern physics, the unification of gravity with quantum mechanics. The Standard Model is a quantum theory, but it does not include gravity. Einstein's general theory of relativity is our best theory of gravity, but it is a classical theory. The search for a quantum theory of gravity that can consistently describe both the very large and the very small is the great unfinished revolution of 20th century physics. Some theories, like string theory, propose a radical solution, the existence of extra hidden dimensions of space. In these theories, the weakness of gravity compared to the other forces could be explained by the fact that gravity is the only force that can leak out into these extra dimensions. The LHC is searching for evidence of these extra dimensions by looking for the production of microscopic black holes or for the signature of Kaluza-Klein particles, the heavy copies of the known particles that would be the result of their vibration in the extra dimensions. The absence of answers to these profound questions is not a sign of failure. It is a sign that we are standing at the threshold of a new and deeper understanding of the universe. The LHC, with its ongoing upgrades and its ever-increasing precision, remains our most powerful tool for probing this new frontier. It is a machine that is designed not just to find answers, but to ask new and more profound questions. And in the subtle anomalies, the unexpected results, the things that don't fit our current theories, may lie the clues that will lead us to the next great revolution in our understanding of the deep, beautiful, and wonderfully mysterious nature of reality. The Standard Model of particle physics is one of the crowning achievements of modern science. It is a beautiful and remarkably successful theory that describes the fundamental subatomic constituents of our universe and the forces that govern their interactions. It is a testament to the power of human reason to uncover the deep mathematical order that underlies the seeming chaos of the physical world. At its core, the Standard Model is a kind of periodic table of the fundamental particles. It organizes the known particles into three fundamental categories. The first are the quarks, which are the building blocks of the protons and neutrons that make up the atomic nucleus. There are 6 flavors of quarks, which come in 3 generations of increasing mass: the up and down quarks, the charm and strange quarks, and the top and bottom quarks. The second category are the leptons, which are the other fundamental matter particles. The most famous of these is the electron, which orbits the atomic nucleus and is responsible for all of chemistry. The electron also has 2 heavier cousins, the muon and the tau, and each of these 3 charged leptons has a corresponding, nearly massless and incredibly elusive partner, the neutrino. The third category are the gauge bosons, which are the particles that mediate the fundamental forces of nature. The photon is the carrier of the electromagnetic force. The gluons are the carriers of the strong nuclear force, the force that binds the quarks together inside protons and neutrons. And the W and Z bosons are the carriers of the weak nuclear force, the force that is responsible for certain kinds of radioactive decay. And finally, there is the Higgs boson, the particle associated with the all-pervading Higgs field, which, as we have seen, is responsible for giving mass to many of the other fundamental particles. This elegant and relatively simple cast of 17 fundamental particles and the mathematical framework of quantum field theory that describes their interactions has been able to explain, with incredible precision, the results of virtually every particle physics experiment that has ever been performed. It is a theory that has been tested and confirmed to an astonishing degree of accuracy. And yet, for all its success, we know that the Standard Model is not the final word. It is an incomplete theory, a beautiful but partial chapter in the grand book of reality. It has a number of profound and glaring omissions. Most famously, it does not include the force of gravity. It has no explanation for the existence of dark matter and dark energy, the mysterious, invisible components that make up 95% of the energy content of the universe. It does not explain the observed asymmetry between matter and antimatter. And it has a number of free parameters, about 19 of them, like the masses of the particles and the strengths of the forces, whose values are not predicted by the theory, but must be measured experimentally. These are not just minor details. They are deep conceptual cracks in the foundation of our current understanding, cracks that point towards the existence of a new and more fundamental layer of physical reality. The search for this new physics beyond the Standard Model is the primary occupation of modern experimental and theoretical particle physics, and there are a number of compelling theoretical ideas that offer a glimpse of what this new physics might look like. One of the most elegant and most popular of these is the idea of supersymmetry, or SUSY. Supersymmetry is a hypothetical, new symmetry of nature that would relate the two fundamental classes of particles, the fermions, which are the matter particles like quarks and leptons, and the bosons, which are the force-carrying particles. In a supersymmetric world, every known fermion would have a corresponding superpartner boson, and every known boson would have a corresponding superpartner fermion. The electron would have a superpartner called the selectron. The quark would have a squark. The photon would have a photino. The Higgs boson would have a Higgsino. This doubling of the particle zoo may seem like a complication, but it is a complication that has the potential to solve a number of the deep problems of the Standard Model at once. For example, the existence of these new supersymmetric particles would naturally and elegantly solve the hierarchy problem, the puzzle of why the Higgs boson is so light. The quantum corrections to the Higgs mass from the Standard Model particles would be almost perfectly cancelled by the contributions from their superpartners, keeping the Higgs mass naturally small and stable. Supersymmetry also provides a natural candidate for the dark matter particle. In most supersymmetric models, the lightest supersymmetric particle is stable, and it would have just the right properties, being massive and interacting only weakly with normal matter to be the dark matter that we observe in the cosmos. And finally, at very high energies, the strengths of the three forces of the Standard Model, when extrapolated using the equations of supersymmetry, seem to converge to a single, unified value, a tantalizing hint of a grand unified theory where the three forces are just different aspects of a single underlying force. For all these reasons, the search for supersymmetry has been one of the primary goals of the Large Hadron Collider. But after more than a decade of searching, the LHC has, so far, found no evidence for these new supersymmetric particles. This has led many to question the validity of the simplest and most natural supersymmetric models, and to explore other, more complex, or more hidden, versions of the theory. Another and equally profound. Idea for physics beyond the standard model is the existence of extra hidden dimensions of space. As we have seen, theories like string theory require the existence of 10 or 11 space-time dimensions to be mathematically consistent. The idea is that the extra spatial dimensions are compactified, curled up into a tiny, and for us, invisible shape. But these extra dimensions could have real, and potentially detectable, physical consequences. They could help to explain the weakness of gravity, and they could provide a home for new particles and new forces. The search for these extra dimensions at the LHC is a search for strange and unexpected experimental signatures, like the production of microscopic black holes, or the observation of a tower of heavy Kaluza-Klein particles, which would be the extra-dimensional copies of the known standard model particles. And then there is the possibility of entirely new and as yet unimagined fundamental forces in particles. The standard model has a very specific and somewhat arbitrary structure. There is no deep theoretical reason why there should be exactly 3 generations of quarks and leptons, or why the forces should have the specific mathematical structure that they do. It is possible that there is a whole new dark sector of particles and forces that is hidden from us, a sector that interacts with our own visible world only through very weak or portal interactions. Dark matter could be a part of this dark sector, and the LHC, with its high energies and its incredible sensitivity, is a powerful tool for searching for the subtle, indirect signatures of this hidden world. The absence of any clear, unambiguous signal of new physics at the LHC beyond the Higgs boson has been a source of both frustration and excitement in the particle physics community. It is frustrating because the simple and elegant solutions to the problems of the standard model, like supersymmetry, have not yet materialized. But it is also exciting because it means that the universe is more subtle, more clever, and more mysterious than we thought. The path to a deeper understanding is not as straightforward as we might have hoped, and it will require a new generation of more powerful experiments, and perhaps a new generation of even more creative and more radical theoretical ideas. The story of the universe is far from over, and the standard model, for all its beauty and its success, is just the beginning of the story. The idea that our familiar or four-dimensional universe may be just a small slice of a much larger and much more complex. Multidimensional reality is one of the most mind-bending and transformative concepts in all of modern physics. It is an idea that has its roots in the early 20th century, but it has been given a new and powerful life by the development of modern unified theories like string theory. The quest to unify gravity with the other forces of nature has led physicists down a path that seems to inevitably point towards the existence of extra hidden dimensions of space. In string theory, the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings. And the mathematical consistency of this theory requires that these strings must be vibrating in a space-time that has more than the 4 dimensions we are familiar with, typically 10 or 11 dimensions in total. So, where are these extra dimensions? Why do we not see them in our everyday lives? The standard answer is that they are compactified, curled up into a tiny, intricate, and for us, invisible, geometrical shape at every point in our 3-dimensional space. Imagine a tightrope walker from a great distance. The rope appears to be a one-dimensional line. The walker can only move forwards or backwards. But for a tiny ant on the rope, there is another and very real dimension, the circular dimension that goes around the rope. The ant can move forwards and backwards, but it can also move around the rope. The extra dimensions of string theory are like this circular dimension of the rope, but they are curled up on a scale that is unimaginably small, the Planck length, which is why we do not perceive them directly. But these extra dimensions are not just a mathematical curiosity. They have profound physical consequences. The precise shape and size of this compact, 6- or 7-dimensional Calabi-Yau manifold is what determines the properties of the strings, and therefore, the properties of all the particles and forces of our universe. The laws of physics are a reflection of the geometry of these hidden dimensions. This is a breathtakingly beautiful and ambitious idea. It suggests that the deep, and often seemingly arbitrary, structure of our universe is a consequence of a hidden, higher-dimensional geometry. But the existence of extra dimensions has also led to another, and equally radical, idea: the brain world scenario. In this picture, our entire 4-dimensional universe is a brain, a subspace that is floating in a higher-dimensional bulk. The particles and forces of the standard model are confined to our brain. They are like drawings on a sheet of paper that cannot leave the surface. But gravity, the geometry of space-time itself, is a property of the entire higher-dimensional bulk, and it is free to propagate through the extra dimensions. This could provide a beautiful and elegant solution to the hierarchy problem. The puzzle of why gravity is so much weaker than the other forces. The gravitational force is not intrinsically weak. It just appears weak to us because its influence is being diluted, spread out over the extra hidden dimensions. Our brain is only feeling a small fraction of its true higher dimensional strength. The brain world scenario opens up a host of new and truly extraordinary cosmological possibilities. There could be other parallel brains, other universes, floating nearby in the bulk, separated from us by a tiny distance in a 5th dimension. This is a different kind of multiverse than the bubble universe picture of eternal inflation. It is a multiverse of stacked, parallel realities. And it is a multiverse that could, in principle, have observable consequences. While we cannot directly travel to these other brains, we could potentially interact with them through the one force that can travel through the bulk gravity. The mysterious, invisible dark matter that fills our universe could be the gravitational influence of ordinary matter that is confined to a nearby parallel brain. We cannot see the matter on that shadow brain because light and the other standard model forces are trapped on it, but we can feel its gravitational pull. The Big Bang itself could have been the result of a collision between our brain and another, a cataclysmic event in the higher dimensional bulk that released the energy to create our entire cosmos. This ekpyrotic, or cyclic model, as we have seen, provides a compelling alternative to the standard inflationary picture of our cosmic origin. The search for evidence of these extra dimensions is one of the most exciting and active frontiers of modern experimental physics. The Large Hadron Collider is at the forefront of this search. If the extra dimensions are large enough, then the high-energy collisions at the LHC could have enough energy to kick a particle off of our brain and into the bulk. This would manifest in the detectors as missing energy, a clear and unambiguous signal that something has escaped from our familiar 4-dimensional world. The LHC could also, in some of these models, have enough energy to create tiny, microscopic black holes. These would not be the dangerous, galaxy-devouring black holes of astrophysics. They would be tiny, fleeting, quantum gravitational objects that would evaporate almost instantly in a shower of Hawking radiation. The detection of such an event would be a stunning and Nobel Prize-winning confirmation of the existence of extra dimensions and a direct window into the strange and beautiful world of quantum gravity. So far, the LHC has found no evidence for either missing energy or microscopic black holes. This has placed tight constraints on many of the simplest and most natural extra-dimensional models, but the search continues. The universe may be more subtle, more clever, and more multidimensional than we have yet been able to probe. The idea of hidden dimensions is a concept that pushes the limits of our scientific imagination. But it is an idea that is born from the deep, mathematical logic of our best and most ambitious physical theories. And it is an idea that reminds us that the reality we perceive with our senses may just be a shadow, a fleeting and partial projection of a much richer, much deeper, and much more wonderfully complex multidimensional cosmos. The idea of a multiverse, a vast and perhaps infinite ensemble of other parallel universes, is one of the most breathtaking, most mind-altering, and also most controversial concepts in all of modern science. It is an idea that has migrated from the pages of science fiction to the blackboards of our most eminent theoretical physicists. And it is an idea that has the potential to fundamentally reshape our understanding of our own cosmic place. The multiverse is not a single, coherent theory, but is a concept that arises in different forms from several of our deepest and most successful physical theories. The many worlds interpretation of quantum mechanics, as we have seen, suggests a constantly branching quantum multiverse, where every possible outcome of every quantum event is realized in a separate, parallel reality. The theory of eternal inflation suggests a bubble universe multiverse, where our own cosmos is just one, local, post-inflationary bubble in a much larger and eternally inflating meta-universe. And the landscape of string theory suggests a multiverse of different possible vacuum states, each with its own unique set of physical laws and constants. While the details of these different multiverse scenarios differ, they all share a common and deeply revolutionary idea that our universe is not the whole of reality. It is just one, small, and perhaps insignificant, part of a much larger and much more diverse cosmic tapestry. This is a vision that is both humbling and intellectually powerful. It is humbling because it represents the final and most profound step in the Copernican revolution, the long historical process of decentering humanity from a special and privileged position in the cosmos. We are not at the center of the solar system. We are not at the center of the galaxy. And we may not even be in the only universe. But the multiverse is also intellectually powerful because it provides a potential scientific explanation for one of the deepest and most puzzling features of our own universe, its apparent and seemingly miraculous fine-tuning for the existence of life, the anthropic principle. In the context of a multiverse, becomes a simple and powerful selection effect. We find ourselves in a universe that is hospitable to life for the same reason that we find ourselves on a planet that is hospitable to life. We could not have found ourselves anywhere else but the primary and most serious objection to the multiverse hypothesis is that it is, by its very nature, untestable. We can never, even in principle, travel to another bubble universe or communicate with a parallel quantum branch. The multiverse seems to lie forever beyond the reach of our direct empirical science. This has led many to argue that the multiverse is not a scientific theory at all, but is a form of metaphysical speculation, a new and more sophisticated version of the ancient religious and philosophical myths of creation. They argue that by embracing an untestable theory, we are in danger of abandoning the very principles of empirical verification that have been the hallmark of the scientific revolution. We are in danger of turning science into a new kind of dogmatic faith. Others, however, argue that this is a naive and overly restrictive view of the scientific method. They argue that a theory should be judged not just by its direct empirical predictions, but also by its explanatory power, its mathematical consistency, its elegance, and its ability to solve the deep conceptual puzzles of our current theories. The multiverse, they argue, for all its strangeness and its untestability, does provide a powerful and perhaps the only naturalistic explanation for the apparent fine-tuning of the physical constants of our universe. In this view, the multiverse is not just a wild speculation. It is a logically necessary consequence of our best current understanding of cosmology and quantum mechanics. The LHC could provide hints of the multiverse in several different ways. The search for extra dimensions is, in a sense, a search for the multiverse. If the LHC were to discover evidence of extra dimensions through the production of microscopic black holes or the detection of missing energy, it would lend powerful circumstantial support to the brain world scenario, a specific and well-defined model of a multiverse. The properties of the Higgs boson itself could also provide a clue. As we have seen, the measured mass of the Higgs seems to place our universe in a metastable vacuum state. In the context of the string theory landscape, this is exactly what one might expect. The vast majority of the possible vacuum states in the landscape are not stable. And so, if universes are populated randomly across this landscape, we should not be surprised to find ourselves in a universe that is long-lived, but not eternally stable. The metastability of our vacuum could be a sign that we are living in a multiverse. The search for new and unexpected particles and forces at the LHC is also a search for the multiverse. If the LHC were to discover a new, long-lived particle or a new, very weak force, it could be a sign of a hidden, dark sector of particles that interacts with our own, visible world only very weakly. And this dark sector could be the matter of a nearby parallel brain or a portal to a different, hidden reality. The most direct, and also most speculative, way that the LHC could probe the multiverse is through the potential production of microscopic black holes. In some brain world models with large extra dimensions, the energy required to create a black hole is much lower than in our familiar four-dimensional spacetime. It is possible that the high-energy collisions at the LHC could have enough energy to create tiny, fleeting quantum black holes. These black holes would not be dangerous. They would evaporate almost instantly in a shower of Hawking radiation. But the specific properties of this radiation, its temperature, its spectrum, could provide us with a direct window into the physics of the extra dimensions, and perhaps even into the nature of quantum gravity itself. So far, the LHC has found no evidence for any of these exotic, multiverse-related phenomena. This has placed tight constraints on many of the simplest and most natural multiverse models, but the search is far from over. The upcoming high-luminosity upgrade of the LHC will increase its sensitivity to rare processes by a factor of 10, opening up a new and much wider window of discovery. And the next generation of even more powerful colliders, like the proposed Future Circular Collider, will push the energy frontier even further. The multiverse is an idea that is on the very edge of our scientific knowledge. It is a concept that is as beautiful and as profound as it is controversial and untestable. It may be that we will never find a definitive, smoking gun proof of its existence. But the search itself, the quest to understand whether our universe is the one and only, or just one of a vast and perhaps infinite cosmic ensemble, is a quest that is at the very heart of the human scientific adventure. It is a quest that is pushing our theories, our experiments, and our very imagination to their ultimate limits. The mysterious, invisible substance known as dark matter is one of the most profound, and also most humbling, puzzles in all of modern science. It is a substance that makes up about 85% of the total matter in the universe, and yet we have no idea what it is. It is the silent, gravitational scaffolding upon which the entire, visible structure of our cosmos is built. And yet, it remains completely and stubbornly invisible to all of our most powerful telescopes. The evidence for the existence of dark matter is overwhelming, and it comes from a host of different and independent astronomical observations. It was first inferred in the 1930s by the Swiss astronomer Fritz Zwicky, who observed that the galaxies in the Coma cluster were moving far too fast to be held together by the gravity of their visible stars alone. He concluded that there must be a huge amount of unseen, dark matter providing the extra gravitational glue. In the 1970s, the American astronomer Vera Rubin made the same startling discovery when she studied the rotation speeds of individual spiral galaxies. She found that the stars in the outer regions of these galaxies were orbiting far too quickly. According to Newton's laws of gravity, their speeds should have dropped off with distance from the galactic center, but they did not. They remained stubbornly high. The only way to explain this was to posit the existence of a vast and invisible halo of dark matter surrounding each galaxy. A halo whose gravitational pull was keeping the outer stars in their high-speed orbits. Since then, the evidence has continued to mount. The way that the gravity of massive galaxy clusters bends and distorts the light from more distant background galaxies, a phenomenon known as gravitational lensing, provides a direct way to map the distribution of mass, and it has confirmed the existence of these vast dark matter halos. The temperature fluctuations in the cosmic microwave background, the afterglow of the Big Bang, also carry a clear and precise imprint of the amount of dark matter in the early universe. All of these different lines of evidence converge on a single and inescapable conclusion: the universe is filled with a new and as yet undiscovered form of matter. A matter that does not interact with light. A matter that is dark. But what is it the standard model of particle physics? Our otherwise incredibly successful theory of the fundamental particles and forces has no place for a dark matter particle. This means that dark matter must be something new, something that lies beyond our current and well-tested understanding of reality. For decades, the leading candidate for the dark matter particle was the weakly interacting massive particle, or WIMP. This was a generic term for a new heavy particle that would interact with normal matter only through the weak nuclear force and gravity. This was an attractive idea for a number of reasons. Firstly, theories beyond the standard model, like supersymmetry, naturally predicted the existence of new, stable, and weakly interacting particles with just the right properties to be the dark matter. And secondly, a WIMP with a specific mass and interaction strength would have been produced in the hot early universe in just the right abundance to account for the observed amount of dark matter today. This WIMP miracle, as it was called, made it the focus of an intense and worldwide experimental search. But after decades of searching, in deep underground laboratories with satellite-based telescopes, and at the Large Hadron Collider, we have found no definitive evidence for WIMPs. The parameter space for the simplest and most natural WIMP models has been almost completely ruled out. This has led to a crisis in the field of dark matter physics, a crisis that has also been a period of immense creative ferment. Physicists are now exploring a whole host of new and more exotic dark matter candidates. Perhaps dark matter is not a WIMP, but an action, a hypothetical, ultralight particle that was originally proposed to solve a different puzzle in the theory of the strong nuclear force. Actions would be incredibly difficult to detect, as they interact with normal matter even more weakly than WIMPs, but a number of clever new experiments are being designed to search for their faint, telltale signature. Or perhaps dark matter is not a single particle, but is part of a whole, hidden dark sector. A complex world of dark particles and dark forces that interacts with our own visible world only through a faint, gravitational portal. The Large Hadron Collider is one of the most powerful tools we have in the search for dark matter. While it may not be able to detect a dark matter particle directly, as these particles would fly straight through the detectors without leaving a trace. It can search for them indirectly. If dark matter particles are produced in the high-energy collisions at the LHC, they will carry away energy and momentum. This would manifest in the detectors as missing energy, a clear and unambiguous imbalance in the energy of the visible particles that are produced in the collision. The search for this missing energy signature is one of the highest priorities of the LHC experimental program. So far, no such signal has been seen, which has placed tight constraints on many dark matter models. But the search continues, and with the upcoming high-luminosity upgrade of the LHC, the sensitivity to these kinds of signatures will be dramatically increased. A more radical and more controversial idea is that dark matter may not be a particle at all. Perhaps our understanding of gravity is wrong. The theory of modified Newtonian dynamics, or MOND, proposes that Newton's law of gravity needs to be modified at very low accelerations, like those found in the outer regions of galaxies. In this view, there is no dark matter. The observed anomalous rotation of galaxies is simply a sign that gravity is stronger than we thought in these regimes. While MOND has had some remarkable successes in explaining the rotation curves of individual galaxies, it has struggled to explain the observations of galaxy clusters and the cosmic microwave background without invoking some form of dark matter. The mystery of dark matter is not just a puzzle for particle physicists and astronomers. It is a profound philosophical challenge to our understanding of reality. It is a humbling reminder that the world we see, the world of stars, of planets, of light, is just a small, and perhaps insignificant, fraction of the true cosmic reality. We are living in a universe whose primary material constituent is completely unknown to us. But could the mystery of dark matter be connected to another, and even deeper, mystery, the existence of parallel universes? This is a speculative but deeply intriguing idea. In the brain world scenarios we have discussed, our universe is a three-dimensional membrane floating in a higher dimensional space. In some of these models, there could be other parallel branes nearby, and it is possible that the dark matter we observe is simply the gravitational influence of ordinary matter that is confined to one of these nearby shadow branes. We cannot see the matter on that other brane because light and the other standard model forces are trapped on it. But we can feel its gravity because gravity is a property of the entire higher dimensional bulk. In this view, dark matter is not a new, exotic particle. It is a ghost, a gravitational echo of a whole other universe that is existing just a hair's breadth away from our own. This is a breathtaking and almost poetic idea. It would mean that the invisible halo of dark matter that surrounds our own galaxy is not just a cloud of unknown particles. It is the gravitational shadow of a parallel, and perhaps even identical, Milky Way galaxy, a galaxy that is sharing our corner of the higher dimensional cosmos. The search for the nature of dark matter is one of the great scientific adventures of our time. It is a quest that is being pursued on multiple fronts, from the deep underground laboratories searching for a single, fleeting particle interaction, to the vast cosmological surveys mapping the large-scale structure of the universe, to the high-energy collisions at the Large Hadron Collider. The resolution of this mystery, whatever it may be, will undoubtedly mark a new and revolutionary chapter in our understanding of the universe, and it is a mystery that serves as a constant and powerful reminder of the vastness of our own ignorance and of the deep, dark, and beautiful secrets that are still waiting to be discovered in the silent, gravitational whispers of the cosmos. The Large Hadron Collider, in its first decade-long run, has been a story of both spectacular triumph and profound and puzzling silence. The triumph, of course. was the discovery of the Higgs boson in 2012, the final missing piece of the standard model of particle physics. A discovery that confirmed our understanding of the origin of mass and completed the beautiful and remarkably successful theoretical edifice that has been built over the last half-century. But the silence has been just as profound. In the years since the Higgs discovery, the LHC has been pushed to higher and higher energies and has collected an immense amount of data. And yet it has so far found no definitive evidence for any of the new physics beyond the standard model that was so confidently predicted by theorists. Supersymmetry, extra dimensions, microscopic black holes, new forces, new particles, all of the elegant and well-motivated. Theoretical solutions to the deep, remaining puzzles of the universe have, so far, failed to materialize. This has led to a period of deep soul-searching, of re-evaluation, and also of immense creative excitement in the world of particle physics. We are standing at a crossroads, a moment where the old, familiar map of reality has run out, and we are venturing into a truly uncharted territory. The search for supersymmetry, or SUSY, has been one of the primary drivers of the LHC experimental program. The theory, as we have seen, is a beautiful and elegant one, and it has the potential to solve a number of the deep problems of the standard model at once, but the simplest and most natural. Versions of supersymmetry predicted that the superpartner particles should have masses that were within the reach of the LHC. The fact that we have not seen them is a major puzzle. This does not necessarily mean that supersymmetry is wrong. It could be that the superpartners are much heavier than we thought and are simply beyond the reach of the current LHC, or it could be that supersymmetry is a more complex and more hidden symmetry than our simplest models predicted. But the absence of any evidence for SUSY has forced physicists to consider other and more unconventional solutions to the hierarchy problem, the puzzle of the Higgs mass, another major and so far fruitless. Search at the LHC has been the search for a particle candidate for dark matter. The WIMP paradigm, which was the leading theoretical framework for decades, has been severely constrained by the lack of any signal at the LHC and in the deep, underground direct detection experiments. This has led to a paradigm shift in the field of dark matter physics, a shift away from the simple, WIMP-centric view and towards a much broader and more diverse landscape of possibilities. The search is now on for actions, for sterile neutrinos, for dark photons, for a whole, hidden, dark sector of particles and forces. This is a much more challenging search, as these new candidates are often much lighter and interact even more weakly than WIMPs, making their signatures at the LHC much more subtle and difficult to detect. But it is a search that is being pursued with a new sense of creativity and urgency. The Higgs boson itself, while a monumental discovery, has also presented us with a new set of puzzles. Its measured properties are, so far, remarkably consistent with the predictions of the standard model. It seems to be a simple, garden-variety Higgs. But is this the whole story? Or is the Higgs boson a portal to a new and hidden sector of physics? Some theories suggest that there could be multiple types of Higgs bosons, a whole Higgs family. Others suggest that the Higgs boson could interact with new, as yet undiscovered, particles, like those of the dark matter sector. The precision study of the properties of the Higgs boson, its mass, its spin, its interactions with all the other known particles, is one of the primary goals of the ongoing LHC program. Any tiny deviation from the predictions of the standard model could be the first telltale sign of the new physics that we know must be there. To push the boundaries of this search, the LHC itself is undergoing a major and ambitious upgrade. The high luminosity LHC, which is scheduled to begin operations in 2029, will not increase the energy of the collider, but will dramatically increase its luminosity, which is a measure of the number of particle collisions that occur per second. The HL-LHC will increase the luminosity by a factor of 10, allowing the experiments to collect a data set that is 10 times larger than the current one. This will be a game changer. It will allow physicists to study extremely rare processes that have never been seen before. It will allow for a much more precise measurement of the properties of the Higgs boson and of the other known particles, and it will dramatically increase the sensitivity of the search for new, high-mass particles and for the subtle, indirect signatures of new physics. The HL-LHC is a machine that is designed to search for the small cracks in the beautiful, but ultimately incomplete, edifice of the Standard Model. But what if the HL-LHC, too, finds nothing new? What if the universe is more subtle, more well-hidden than even this powerful new machine can reveal? This is a possibility that the physics community is now beginning to seriously grapple with, and it has led to the planning of the next generation of even larger and more powerful particle colliders. The Future Circular Collider is one such proposal, a massive 100-kilometer ring that would be capable of reaching collision energies that are nearly 10 times higher than the LHC. Another complementary proposal is the International Linear Collider, a machine that would collide electrons and their antimatter counterparts, positrons, with incredible precision. A linear collider would not reach the same raw energies as a large circular proton collider like the FCC, but it would provide a much cleaner experimental environment, allowing for incredibly precise measurements of the properties of particles like the Higgs boson. The future of particle physics is at a crossroads. The easy, low-hanging fruit of the Standard Model has been picked. The path forward, into the deep and largely unknown territory beyond the Standard Model, is likely to be a long and challenging. 1. It will require a new generation of more powerful machines, a new level of global collaboration, and perhaps a new and more radical way of thinking about the fundamental nature of reality. But it is a journey that we must take. The mysteries of dark matter, of quantum gravity, of the origin of our own material existence are too deep, too profound, and too beautiful to be left unanswered. The LHC has opened a new window onto the universe, and what we have seen so far is just a glimpse of the vast and wonderfully mysterious landscape that still lies ahead. The Large Hadron Collider has already reshaped our understanding of the universe, but its next phase, the high-luminosity LHC, promises to push the boundaries of physics even further. Scheduled to become fully operational in 2029, this ambitious upgrade represents the next evolution in particle physics experimentation. This upgrade will not just increase the energy of the collisions, but will dramatically enhance the luminosity of the collider, a measure of the number of particle collisions that can be produced per second. The HL-LHC will increase the collision rate by a factor of 10, allowing the experiments to collect a data set that is 10 times larger than all the data collected in the first decade-long run of the LHC. This is a crucial step forward. In the world of high-energy physics, more data translates directly to more precision, and more precision translates to a greater chance of discovering new and subtle physical phenomena. Many of the processes that are predicted by theories beyond the Standard Model, such as the production of supersymmetric particles or the effects of extra dimensions, are expected to be extremely rare, occurring perhaps only once in every trillion collisions. To have any hope of observing these fleeting events, scientists need to create a truly astronomical number of collisions. The HL-LHC is a machine that is designed to do exactly that. It is a rare process factory, a powerful tool designed to search for the proverbial needle in a cosmic haystack. One of the primary scientific goals of the HL-LHC is to study the Higgs boson with unprecedented precision. The discovery of the Higgs in 2012 was a monumental achievement, but it was just the beginning of the story. We know that the Higgs boson exists, but we still know very little about its true nature. Is it a single, fundamental particle, as the Standard Model predicts? Or is it a composite object made of other, more fundamental constituents? Is it part of a larger, more complex Higgs sector with other, as yet undiscovered, Higgs-like particles? The HL-LHC will allow physicists to measure the properties of the Higgs, its mass, its spin, its interactions with all the other known particles, with a precision that is an order of magnitude better than what is currently possible. Any tiny deviation from the predictions of the Standard Model would be a smoking gun signal of new physics, a window into the reality that lies beyond our current understanding. The HL-LHC will also dramatically increase our sensitivity to the search for new, high-mass particles. If theories like supersymmetry are correct, but the new superpartner particles are simply too heavy to have been produced in significant numbers at the current LHC. The huge increase in the number of collisions at the HL-LHC will give us a much better chance of seeing them. The search for the elusive dark matter particle will also be a major focus of the HL-LHC program. The upgraded collider will be able to search for a much wider range of dark matter candidates, and with much greater sensitivity than the current LHC. The search for the missing energy signature of dark matter production will be pushed to new limits, and new, more subtle. Search strategies will be employed to try and catch a glimpse of this invisible and mysterious component of our universe. The technological challenges of upgrading the LHC to its high luminosity configuration are immense. It is a project that is pushing the very limits of modern accelerator and detector technology. It requires the development of new, more powerful, and more compact superconducting magnets to focus the proton beams down to an even smaller size at the collision points. It requires a new generation of crab cavities, a special kind of radio frequency cavity that can tilt the proton bunches just before they collide to maximize their overlap and the collision rate. And it requires a complete and ambitious upgrade of the giant detectors, Atlas and CMS. These detectors will need to be equipped with new, more granular, and more radiation-resistant sensors that can handle the incredible and unprecedented data rates of the HL-LHC. This is a monumental engineering endeavor, an endeavor that is requiring a new level of innovation, of ingenuity, and of global scientific collaboration. But the potential scientific payoff is enormous. The HL-LHC will be one of the most important scientific projects of the coming decades. A machine that has the potential to rewrite the laws of physics and to answer some of the most fundamental questions about the nature of our universe. It may be the machine that finally discovers the dark matter particle, that finds the first evidence of supersymmetry, that reveals the existence of extra dimensions, or that uncovers a whole new and completely unexpected layer of physical reality. But even if the HL-LHC finds nothing new, even if the Standard Model continues to hold up to every new and more precise test, that in itself would be a profound and deeply puzzling result. It would mean that the solutions to the deep problems of the Standard Model lie at an energy scale that is far beyond the reach of any conceivable future accelerator. It would mean that we may need a completely new and more radical theoretical paradigm to make progress. It might even mean that we are beginning to approach a fundamental limit to our ability to probe the universe with our current reductionist methods. The HL-LHC is a bet. A bold and ambitious bet on the future of particle physics. It is a bet that the universe still has new and discoverable secrets to reveal at the energy scale that we can access. And it is a bet that the human quest for knowledge, for a deeper understanding of our cosmic home, is a journey that is still far from over. The discoveries that are made at the HL-LHC in the coming decades will undoubtedly reshape our understanding of the universe in ways that we cannot yet imagine, and will set the course for the next generation of scientific exploration. The quest to understand the fundamental nature of reality is a journey that will not end with the Large Hadron Collider, or even with its high luminosity upgrade. The human spirit of discovery is a relentless one. And physicists are already dreaming of and planning for the next generation of even larger and more powerful scientific instruments, machines that will be able to push the frontiers of our knowledge to new and currently unimaginable energy scales. One of the most ambitious of these proposals is the Future Circular Collider, a project that is currently being studied at CERN. The FCC would be a true scientific behemoth, a 100-kilometer-long underground ring, almost 4 times the size of the current LHC. Such a machine would be capable of reaching collision energies that are about 7 times higher than the LHC, opening up a vast and largely unexplored new territory for discovery. The FCC is envisioned as a multi-stage project. The first stage would be an electron-positron collider, a Higgs factory that would be able to produce millions of Higgs bosons in a very clean and well-understood experimental environment. This would allow for incredibly precise measurements of the properties of the Higgs, a search for any tiny deviation from the predictions of the standard model that could signal the existence of new physics. The second stage would be a high-energy proton-proton collider, a true discovery machine that would be able to directly search for new heavy particles up to an energy scale that is far beyond the reach of the LHC. If supersymmetry or extra dimensions or a new heavy force of nature exists, the FCC would be our best hope of finding it. Another and complementary proposal is the International Linear Collider, a project that is being championed by a global collaboration of scientists. The ILC would not be a circular machine, but a linear one, about 30 kilometers long, that would collide electrons and positrons with very high precision. A linear collider cannot reach the same raw energies as a large circular proton collider like the FCC, but it has a key advantage: the collisions are much cleaner. When protons, which are composite objects made of quarks and gluons, collide, they create a very messy and complex spray of particles, an electron-positron collision. On the other hand, is a much simpler and more well-defined interaction, which allows for incredibly precise measurements of the properties of the particles that are produced. The ILC would be a powerful precision tool for studying the Higgs boson and for searching for the subtle, indirect signatures of new physics. But the future of fundamental physics is not just about building bigger and bigger colliders. It is also about exploring new and more innovative ways to probe the secrets of the universe. The growing field of astroparticle physics is a beautiful example of this. It is a field that uses the universe itself as a laboratory. High-energy cosmic rays, neutrinos, gamma rays, gravitational waves. These are the particles that are produced in the most extreme and energetic environments in the cosmos. In supernovae, in neutron star collisions, in the hearts of active galaxies. By studying these cosmic messengers with a new generation of powerful ground-based and space-based detectors, we can probe the laws of physics at energies and in conditions that are far beyond the reach of any terrestrial accelerator. The search for the nature of dark matter is a prime example of this synergistic approach. while the LHC is searching for the production of dark matter particles in high-energy collisions. A host of other experiments are searching for them in different ways. Deep. Underground detectors are trying to catch the rare, fleeting signal of a dark matter particle from our galaxy's halo bouncing off an atomic nucleus. Telescopes are searching for the faint, gamma-ray glow of dark matter particles annihilating each other in the dense center of our galaxy. And cosmological surveys are mapping the distribution of dark matter on the largest scales, providing crucial clues to its properties and its history. The quest to unify gravity and quantum mechanics is another area where a multi-pronged approach is essential. While a future, high-energy collider may one day find the first direct evidence of new quantum gravitational physics, our best hope for probing this realm in the near future may come from the precision study of the cosmos itself. The search for the faint, primordial signature of gravitational waves from the period of cosmic inflation in the cosmic microwave background is a direct window into the physics of the very early and very high-energy universe, and the study of black holes, both with electromagnetic telescopes and with gravitational wave detectors, is providing us with a unique and powerful laboratory for testing the predictions of general relativity in the strong field regime, the very place where we expect the first subtle signs of its breakdown to appear. And finally, the future of fundamental physics will be increasingly intertwined with the development of new and more powerful computational tools. The vast amounts of data that will be generated by the next generation of experiments will require a new level of computational power and a new generation of sophisticated, AI-driven algorithms to analyze. And the development of practical, large-scale quantum computers could, one day, revolutionize the field of theoretical physics, allowing us to perform simulations of complex quantum systems, like the dynamics of a quark-gluon plasma or the quantum geometry of spacetime itself, that are completely intractable on a classical computer. The future of our quest to understand the universe is a bright and incredibly exciting one. It is a future that will be driven by a rich and diverse ecosystem of different and complementary, experimental and theoretical approaches. It is a future that will require a new level of global collaboration, of long-term vision, of scientific creativity. And it is a future that holds the promise of answering some of the deepest, most profound, and most beautiful questions that humanity has ever asked. The idea of a multiverse, a vast and perhaps infinite ensemble of other parallel universes, is one of the most breathtaking, most mind-altering, and also most controversial concepts in all of modern science. It is an idea that pushes the very limits of our imagination and also of our scientific methodology. If these other universes exist, they are, by their very nature, likely to be forever beyond the reach of our direct observation and experimentation. And so, the question arises if the multiverse is a theory that can never be proven. What does that mean for the future of physics? Does it signal a fundamental limit to our ability to understand the cosmos, or does it require us to adopt a new and more philosophical understanding of what constitutes a scientific theory? The multiverse is not a single, speculative idea that has been pulled out of thin air. It is a concept that arises, naturally and almost inevitably, from several of our best and most well-tested physical theories. The many worlds interpretation of quantum mechanics, the theory of eternal cosmic inflation, the landscape of string theory, all of these different and well-developed theoretical frameworks seem to point towards the same radical conclusion that our universe is not the one and only. This is a powerful and deeply compelling convergence of ideas. When multiple independent lines of theoretical inquiry all point towards the same surprising conclusion, it is a sign that we should take that conclusion seriously, even if it is a conclusion that challenges our most basic common sense intuitions, but the untestable and perhaps unfalsifiable. nature of the multiverse remains a profound and deeply problematic challenge. Science, in its standard form, is a discipline that is based on empirical evidence. A theory is considered scientific to the extent that it makes testable and falsifiable predictions. The multiverse, in its grandest conception, seems to fail this test. This has led to a deep and often contentious debate within the physics and philosophy of science communities. Some argue that the multiverse is not a scientific theory at all, but is a form of metaphysical speculation, a new and more sophisticated version of the ancient religious and philosophical myths of creation. They argue that by embracing an untestable theory, we are in danger of abandoning the very principles of empirical verification that have been the hallmark of the scientific revolution. We are in danger of turning science into a new kind of dogmatic faith. Others, however, argue that this is a naive and overly restrictive view of the scientific method. They argue that a theory should be judged not just by its direct empirical predictions, but also by its explanatory power, its mathematical consistency, its elegance, and its ability to solve the deep conceptual puzzles of our current theories. The multiverse, they argue, for all its strangeness and its untestability, does provide a powerful, and perhaps the only, naturalistic explanation for the apparent fine-tuning of the physical constants of our universe. In this view, the multiverse is not just a wild speculation. It is a logically necessary consequence of our best current understanding of cosmology and quantum mechanics. But what if no evidence, either direct or indirect, for the multiverse is ever found? What if, after decades of searching, the cosmic microwave background remains stubbornly smooth? The LHC finds no sign of extra dimensions or microscopic black holes, and the fundamental constants of nature continue to appear as single, unexplained numbers. This would not necessarily mean that the multiverse does not exist. It could simply mean that its effects are too subtle, too well hidden for our current, and even our future, experiments to detect. But it would undoubtedly lead to a period of deep crisis and reevaluation in theoretical physics. It would force us to confront the possibility that we may have reached a fundamental limit to our ability to probe the ultimate nature of reality. It would force us to ask a difficult and deeply uncomfortable question: what if the universe is just the way it is, and there is no deeper reason why? This is a possibility that many scientists are reluctant to accept. The entire history of science has been a history of finding deeper and more unified explanations for the phenomena of the natural world. To accept that the fundamental properties of our universe are just a random, accidental set of numbers with no underlying logical or physical explanation seems like a betrayal of the very spirit of the scientific enterprise. It would be a return to a kind of pre-scientific, magical thinking where the world is just a collection of unexplained, brute facts. This is why the search for a final bootstrap theory, a theory of everything that would uniquely and necessarily determine all the properties of our universe, remains such a powerful and enduring dream. But what if this dream is also an illusion? What if the universe is not a unique mathematical necessity, but is in fact just one of a vast and perhaps infinite number of possibilities? The absence of any evidence for the multiverse would not prove that it does not exist, but it would perhaps force us to adopt a new and more humble stance towards our own scientific knowledge. It would force us to accept that there may be certain fundamental questions about the ultimate nature of reality that are, in principle, unanswerable. It would force us to embrace a kind of learned ignorance, a recognition that the universe is not a puzzle to be solved, but a mystery to be lived. The debate over the multiverse is not just a debate about the nature of the cosmos. It is also a debate about the nature of science itself. It is a debate about the limits of our knowledge, about the role of evidence, of theory, of philosophy, of aesthetics, in our quest to understand the universe. And it is a debate that is likely to continue for a long time to come. But whatever the ultimate outcome, the very fact that we are able to have this debate, that we are able to conceive of realities that are so far beyond our own direct experience, is a testament to the remarkable and perhaps even cosmic power of the human mind. The search for the multiverse, whether it ultimately succeeds or fails, is a search that is pushing us to be better scientists, better philosophers, and perhaps even better and more humble human beings. The Large Hadron Collider, in its relentless and powerful probing of the subatomic world, has been a story of both profound discovery and of deep and deepening mystery. The discovery of the Higgs boson in 2012 was a triumph of human ingenuity, a beautiful confirmation of the standard model of particle physics, and a moment that seemed to bring us to the very threshold of a complete understanding of the known, visible universe. But in the years since, the LHC has also given us a profound and puzzling silence. The new physics that was so confidently expected to lie just around the corner, the elegant symmetry of supersymmetry, the strange geometry of extra dimensions, the ghostly particles of dark matter has, so far, failed to appear. This has led some to wonder if we are approaching the end of physics, a point where our current collider-based methodology has reached its fundamental limits. But this is a deeply pessimistic and likely incorrect view. The absence of new discoveries at the LHC is not a sign that there is no new physics to be found. It is a sign that the new physics is more subtle, more well-hidden, and perhaps more strange than our simplest and most natural theories predicted. The universe is not a puzzle that gives up its secrets easily, and the quest to understand it is a long and often winding journey. A journey that is full of both exciting breakthroughs and long periods of patient and often frustrating exploration. The Higgs boson itself, while confirming the standard model, has also opened up a new and largely unexplored landscape of questions. Is it a fundamental, point-like particle, or is it a composite object made of other, more fundamental constituents? Is it the only Higgs boson, or is it part of a larger, more complex Higgs sector? Does it interact with the mysterious dark sector of the universe? The detailed, precision study of the properties of the Higgs boson is one of the primary goals of the ongoing LHC program and of its upcoming high-luminosity upgrade. Any tiny deviation from the predictions of the standard model could be the first telltale sign of the new physics that we know must be there. The mystery of dark matter remains one of the greatest and most humbling challenges in all of science. The failure to find a WIMP particle at the LHC and in the direct detection experiments has forced the field to cast a much wider net, to explore a whole new zoo of more exotic and more difficult to detect dark matter candidates. This is a search that will require a new generation of more sensitive experiments and a new level of creativity and ingenuity from both theorists and experimentalists. And the ultimate mystery, the unification of gravity with quantum mechanics, is a challenge that will likely require a new and more powerful generation of particle accelerators, machines like the proposed Future Circular Collider that can probe the energy scales where the effects of quantum gravity are expected to become apparent. But the future of fundamental physics is not just about building bigger and bigger machines. It is also about exploring new and more complementary avenues of inquiry. The growing field of astroparticle physics, which uses the universe itself as a laboratory, is providing a new and powerful window onto the fundamental laws of nature. The precision study of the cosmic microwave background, the detection of gravitational waves, the search for high-energy neutrinos from distant astrophysical sources, all of these are providing crucial and often unique clues to the physics that lies beyond our current understanding. The story of our universe, as revealed by the LHC and by all our other scientific explorations, is a story that is still being written. We have learned an immense amount in the last century, but we have also learned the true and vast extent of our own ignorance. We have discovered that the universe we see, the universe of atoms, of stars, of galaxies, is just a tiny 5% fraction of the true cosmic reality. The rest is a dark and largely unknown world of dark matter and dark energy. We have discovered that our universe may have been born from a mysterious and perhaps eternal multiverse. We have discovered that the very fabric of our reality, the space and the time that we inhabit, may be a fragile and perhaps even temporary illusion. These are discoveries that should not lead us to a sense of intellectual despair, but to a feeling of profound and beautiful humility. They are a reminder that we are not the masters of the universe, but are just a small and very young species, just beginning to wake up to the true and breathtaking scale and strangeness of our cosmic home. The quest for knowledge is a long and perhaps infinite one, and the Large Hadron Collider, for all its power and its glory, is just one small step on this grand and unending human adventure, the greatest discoveries, the most profound revelations. The answers to the deepest questions that humanity has ever asked may still lie ahead, waiting for us in the deep, dark, and wonderfully mysterious heart of the subatomic world. The Large Hadron Collider is more than just a powerful machine. It is a symbol of our species' insatiable curiosity, a testament to our relentless drive to understand the fundamental nature of the universe. It is a modern-day cathedral, a place where thousands of scientists from all over the world come together to ask the biggest and most profound questions. And while the LHC has already delivered one of the greatest scientific triumphs of our time, the discovery of the Higgs boson, its work is far from over. The search for answers to the deep, remaining mysteries of the cosmos continues, and the LHC, with its ongoing upgrades and its ever-increasing power, remains at the very forefront of this grand human endeavor. The mystery of dark matter is one of the primary targets of the ongoing LHC program. While the simplest WIMP candidates have not been found, the search has now expanded to a much wider and more diverse range of possibilities. The LHC is searching for the signatures of action-like particles, for the production of sterile neutrinos, for the subtle and often hidden signals of a whole new dark sector of particles and forces. This is a challenging and painstaking search, a process of sifting through a mountain of data for a tiny and often ambiguous signal. But it is a search that is driven by the profound realization that the vast majority of the matter in our universe is still completely unknown to us. The puzzle of the matter-antimatter asymmetry is another and equally profound mystery that the LHC is uniquely positioned to address. The LHC-B experiment, one of the 4 large detectors at the LHC, is specifically designed to study the subtle differences in the behavior of matter and antimatter by precisely measuring the decays of particles that contain beauty quarks. Any tiny deviation from the predictions of the standard model in these decays could be the first crucial clue to the new source of CP violation that is needed to explain our own matter-dominated existence. The search for extra hidden dimensions of space is another, and more speculative, but also more exciting, avenue of research at the LHC. The detection of microscopic black holes, or of a tower of heavy Kaluza-Klein particles, would be a discovery of revolutionary and almost unimaginable significance. It would prove that our familiar four-dimensional reality is just a small slice of a much larger and much more complex, multidimensional cosmos, and it would open up a whole new and previously hidden landscape for scientific exploration. The possibility of a multiverse is perhaps the most mind-bending, and also most controversial, of all the ideas that the LHC is capable of probing. While a direct detection of another universe is impossible, the LHC could provide crucial indirect evidence. A discovery of supersymmetry, or of extra dimensions, would lend powerful circumstantial support to the string theory landscape and the brain world scenarios, both of which naturally lead to the idea of a multiverse. And the precision measurement of the properties of the Higgs boson could tell us whether our own universe's vacuum is stable or metastable, a clue that could point towards our place in a larger cosmic ensemble of different possible vacuum states. The quest for new physics at the LHC is a quest that is being pushed to new limits by the ambitious and technically challenging high-luminosity LHC upgrade. This is a project that will transform the LHC into an even more powerful discovery machine. A machine that will be able to produce a dataset that is 10 times larger than anything we have collected so far. This huge increase in luminosity, in the number of collisions, will allow physicists to search for extremely rare processes that are simply inaccessible at the current LHC. It will be like turning up the brightness on our picture of the subatomic world, allowing us to see the faint and subtle details that have so far been hidden in the noise. The LHC will be a Higgs factory, producing millions of Higgs bosons and allowing for an incredibly precise measurement of their properties. It will be a dark matter hunter, with a much greater sensitivity to a wide range of dark matter candidates. And it will be a new physics explorer, with the potential to discover new particles, new forces, and new symmetries of nature that could revolutionize our understanding of the universe. But the future of particle physics does not end with the LHC. The global scientific community is already planning for the post-LHC era, for the next generation of even larger and more powerful particle accelerators that will be needed to push the energy frontier even further. The Future Circular Collider is one such proposal, a massive 100-kilometer ring that would be capable of reaching collision energies that are nearly 10 times higher than the LHC. The Compact Linear Collider is another. These are machines that will not be built for decades, but they are a testament to the long-term vision, the ambition, and the enduring curiosity of the human spirit. The search for the fundamental truths of the universe is a long and often difficult journey. It is a journey that is full of both exciting breakthroughs and long periods of patient and sometimes frustrating exploration. And it is a journey that requires a deep and unwavering commitment to the power of science, of reason, of collaboration, to unravel the deep and beautiful secrets of the cosmos. The Large Hadron Collider and the machines that will come after it are more than just scientific instruments. They are symbols of our species' highest aspirations. They are the modern-day pyramids, the cathedrals of our time, monuments to our collective desire to understand our place in the universe, to ask the biggest questions, and to dare to seek the answers. The journey is far from over. The greatest mysteries, the most profound discoveries, the answers to the questions that have haunted humanity since the dawn of consciousness may still lie ahead, waiting for us in the deep, dark, and wonderfully mysterious heart of the subatomic world. Scientists just broke a record that could change how we see the universe forever. Using the Chinese quantum satellite, known as Microcosm, they managed to link particles' photons of light across a mind-boggling distance of over 1,200 kilometers. These particles became entangled, a strange and wonderful quantum state where they influence each other instantly, even though they were separated by a vast expanse of space. This is not just a cool experiment. It is a profound glimpse into how the very fabric of the universe might be woven together by invisible, instantaneous, quantum threads. Albert Einstein, one of the greatest minds in history, could never accept this idea. He famously called entanglement spooky action at a distance, dismissing it as an impossibility, a sign that our understanding of quantum mechanics must be incomplete. But this groundbreaking experiment, and many others like it, have proven that the spookiness is real. Entanglement works exactly as the bizarre, counterintuitive rules of quantum physics predict. Imagine pulling a string on Earth and instantly feeling a tug on Mars, with no delay, no signal traveling between the two. That is the essence of quantum entanglement, a phenomenon so strange that it challenges our most deeply held intuitions about space, about time, and about the nature of reality itself. But why does this matter for something as grand as space exploration? The immediate, practical implications are revolutionary. This discovery could be the key to creating unhackable quantum communication systems. Imagine being able to send a perfectly secure message from Earth to a future colony on Mars, or to a distant spacecraft exploring the outer solar system, with the knowledge that any attempt to eavesdrop would be instantly detected. This is not science fiction. It is the promise of a quantum internet, a new kind of communication network built on the strange and wonderful rules of entanglement. But on a deeper, more philosophical level, this experiment hints at something even more profound. It suggests that the space between the stars may not be as empty as it seems. There could be a hidden layer of reality, a web of quantum connections that stretches across the entire universe, linking distant galaxies, stars, and perhaps even living beings, in ways we are only just beginning to understand. It is a vision of a cosmos that is not a collection of separate, isolated objects, but a single, vast, and deeply interconnected quantum system. At its heart, quantum mechanics is the science of the very small, the theory that describes how the fundamental building blocks of our universe, the electrons, the photons, the quarks behave, and their behavior is nothing like the predictable, clockwork world of our everyday experience. Unlike the solid, definite objects of classical physics, quantum particles are creatures of probability and potential. They can exist in multiple states at once, a phenomenon known as superposition. They can make seemingly random decisions about their properties only when they are observed. And, as we have seen, they can be linked together through entanglement, their fates intertwined across vast, cosmic distances. This quantum strangeness is not just a laboratory curiosity. It is the very engine that drives the cosmos. The stars in our sky shine because of a quantum phenomenon called tunneling, a process that allows the nuclei of atoms in the sun's core to overcome their mutual repulsion and fuse together, releasing the immense energy that powers our world. Without quantum tunneling, there would be no sunlight, no energy, no life. The very atoms that make up our bodies are stable only because of the strange, probabilistic rules of the quantum world, which prevent electrons from spiraling into the nucleus. And now, scientists are beginning to explore how these same quantum principles might explain some of the greatest mysteries in all of cosmology. Could quantum entanglement be the key to understanding the bizarre, information-scrambling nature of black holes? Those enigmatic objects where space and time are warped beyond all recognition. Could the ghostly, non-local connections of the quantum world help us to finally unravel the secrets of dark matter, the invisible substance that makes up most of the universe's mass? And could quantum mechanics hold the answer to one of the most mind-bending ideas in all of science? The possibility that our entire three-dimensional universe is a kind of cosmic hologram, a projection of information from a lower-dimensional reality. The Microcosm satellite experiment is just the beginning of this grand and exciting journey. With each new discovery, with each new successful test of the strange and beautiful rules of the quantum world, we are peeling back another layer of reality, revealing a universe that is more interconnected, more mysterious, and more wonderful than we ever dared to imagine. And who knows, the next great breakthrough might not just change how we see the cosmos. It might fundamentally redefine the nature of reality itself. In the strange and beautiful landscape of modern physics, black holes spawned as the ultimate enigma, a place where the two great pillars of our understanding, Einstein's general theory of relativity and the laws of quantum mechanics, collide in a storm of paradox and mystery. For decades, we have seen black holes as purely astrophysical objects, the collapsed remnants of massive stars, gravitational behemoths whose immense pull warps the very fabric of space-time. But a new and revolutionary picture is beginning to emerge, a picture that suggests that these cosmic monsters are not just objects in the quantum world, but are, in a very real sense, quantum objects themselves. A groundbreaking new study has proposed that some of the very first black holes, the primordial black holes that are thought to have formed in the turbulent, fiery moments following the Big Bang, may carry with them a unique quantum fingerprint. This theory suggests that these ancient black holes might exhibit properties that are influenced by quantum chromodynamics, QCD. The theory that describes the strong nuclear force, the force that binds quarks and gluons together inside protons and neutrons. This is a staggering idea. It implies that a black hole is not just a region of curved spacetime, but is deeply and intimately tied to the fundamental quantum fields that govern the smallest scales of reality. This is a vision of a black hole as a kind of cosmic atom, a macroscopic object whose properties are dictated by the bizarre and often counterintuitive rules of the subatomic world. This new quantum view of black holes is inextricably linked to one of the most profound and important ideas in all of theoretical physics: Hawking radiation. In the 1970s, the brilliant physicist Stephen Hawking, in a stunning intellectual achievement, showed that black holes are not completely black due to the constant jittery fluctuations of the quantum vacuum near a black hole's event horizon, the point of no return. Pairs of virtual particles are constantly being created. Occasionally, one of these particles will fall into the black hole, while its partner escapes into space, carrying away a tiny amount of the black hole's mass energy. This slow, steady leakage of energy, now known as Hawking radiation, means that black holes are not eternal prisons of matter and information. They slowly evaporate over immense, almost unimaginable timescales, eventually disappearing in a final, brilliant flash of radiation. Detecting this faint, thermal glow from a real astrophysical black hole remains a significant and perhaps insurmountable experimental challenge. But scientists have found a clever way to study this phenomenon in the laboratory. By creating analog black holes, systems that mimic the properties of an event horizon, they have been able to observe effects that are remarkably similar to Hawking radiation. One of the most promising of these approaches involves using Bose-Einstein condensates, an exotic state of matter where millions of ultra-cold atoms behave as a single, coherent quantum entity. By manipulating these condensates with lasers, physicists can create a region where sound waves, or phonons, can enter but cannot escape, a sonic event horizon. And they have observed the spontaneous emission of phonon pairs from this horizon, a sonic analog of Hawking radiation. While this is not a direct detection of the cosmic phenomenon, it is a powerful confirmation of the underlying theoretical principles, and it gives us confidence that Hawking's strange and beautiful idea is a real feature of our universe. Another, more direct, way to search for the quantum origins of black holes is to look for their fossilized imprints in the oldest light of the universe, the cosmic microwave background, CMB. The theory of cosmic inflation, as we have seen, proposes that the universe underwent a period of hyper-accelerated expansion in its first moments. During this period, tiny primordial quantum fluctuations in the density of the early universe would have been stretched to astronomical scales. In regions where these fluctuations were particularly large, the density could have been high enough for the region to collapse directly into a primordial black hole, bypassing the usual stellar collapse pathway. These primordial black holes, if they exist, would be a direct relic of the quantum nature of the infant universe, and they would have left a subtle but potentially detectable signature in the cosmic microwave background. They would act as gravitational lenses, slightly distorting the path of the ancient light as it traveled towards us, creating specific, localized patterns of temperature and polarization in the CMB. The search for these primordial black hole signatures is one of the most exciting frontiers in observational cosmology, a quest to find the fossilized remnants of the universe's first and most quantum objects. This idea is further supported by another, more recent, cosmic puzzle. Our most powerful telescopes, like the James Webb Space Telescope, have been discovering a surprising number of supermassive black holes in the very early universe, in galaxies that are seen as they were just a few 100 million years after the Big Bang. According to our traditional theories of black hole growth, which involve the slow accretion of gas and the occasional merger with other black holes, there simply has not been enough time for these black holes to grow so large, so quickly. The existence of these ancient cosmic behemoths suggests that they may not have started as small stellar mass black holes. They may have started from much larger and primordial black holes, formed directly from the quantum fluctuations of the early universe, are the perfect candidates for these seeds. This is a beautiful and elegant idea. It suggests that the largest, most massive objects in the universe today may have their origins in the smallest, most fundamental quantum processes of the very beginning of time. It is a direct and powerful link between the quantum and the cosmos. The new and revolutionary field of gravitational wave astronomy is also providing a powerful new window into the quantum nature of black holes. The Laser Interferometer Gravitational Wave Observatory. LIGO and its international partners have now detected the faint, almost imperceptible ripples in space-time from dozens of black hole mergers. These gravitational waves are a direct and beautiful confirmation of Einstein's theory of general relativity. But as scientists have begun to analyze the detailed shape of these waves, the ring-down signal as the two black holes settle into a single final object, they have found subtle hints, subtle echoes, that may not be explained by classical general relativity alone. These echoes could be a sign of quantum effects at the event horizon, a quantum fuzziness that is not present in the classical picture. They could be the result of quantum tunneling near the event horizon, or of the complex quantum gravitational interplay that occurs when two of these massive quantum objects merge. While these findings are still preliminary and highly debated, they represent one of our first tentative glimpses into the realm of quantum gravity, the long sought-after theory that will unite the two great pillars of modern physics. The theoretical study of the quantum vacuum itself also provides clues. The intense gravitational field near a black hole's event horizon is predicted to warp the quantum vacuum in a dramatic way, a phenomenon known as vacuum polarization. This can lead to the spontaneous creation of real particle-antiparticle pairs from the vacuum, a process that is related to, but distinct from, Hawking radiation. Experiments in our most powerful particle accelerators, which can create incredibly strong electromagnetic fields, have observed analogous effects, strengthening our confidence that these quantum vacuum effects are a real and important part of black hole physics. They suggest that a black hole is not a passive, dead object, but is in a constant dynamic dialogue with the quantum vacuum that surrounds it, a dialogue that shapes its properties and its evolution. Another remarkable insight has emerged from the study of gamma-ray bursts, the most powerful and energetic explosions in the universe. These fleeting, brilliant flashes of high-energy radiation are often associated with the formation of a new black hole, either from the collapse of a massive star or the merger of two neutron stars. But some theoretical models suggest that they could also be the signature of the final explosive death of a primordial black hole as it evaporates completely through Hawking radiation. As a small primordial black hole reaches the end of its life, its temperature would skyrocket, and it would release its remaining mass in a final, brilliant burst of gamma rays. Observatories like NASA's Fermi Gamma Ray Space Telescope are constantly scanning the skies for such a distinctive final moment signal, a signal that would be a definitive confirmation of both the existence of primordial black holes and the reality of Hawking radiation. The deep connection between black holes and quantum information is perhaps the most profound and fruitful area of research in all of theoretical physics. The black hole information paradox, the apparent conflict between the prediction that information is lost in a black hole and the quantum principle that information can never be destroyed, has been a major driver of progress for decades. And the proposed solutions to this paradox have led to some of our most radical and revolutionary ideas about the nature of reality. The idea of black hole complementarity and the holographic principle suggest that the information is not lost, but is scrambled and encoded on the two-dimensional event horizon. And some have even proposed that the remnants of evaporated black holes, tiny, Planck-sized objects, could serve as a kind of cosmic memory bank, storing the quantum information of the matter that formed them. While these are highly speculative ideas, they are not without potential observational consequences. These quantum remnants, if they exist, would have a gravitational influence, and their presence could be inferred from their effect on the clustering of galaxies or through their subtle microlensing effect on the light from distant stars. And this brings us back to one of the greatest and most tantalizing mysteries of all, the nature of dark matter. Could the mysterious, invisible substance that makes up most of the universe's mass be nothing more than a vast population of primordial black holes? Forged in the quantum chaos of the early universe, the European Space Agency's Gaia mission, which is mapping the positions and motions of over 1 billion stars in our galaxy with unprecedented precision, could provide a definitive answer to this question. By looking for the telltale, microlensing signatures of these ancient quantum objects, Gaia may one day reveal that the dark gravitational scaffolding of our cosmos is a direct and beautiful legacy of the universe's quantum origins. The interplay between the quantum fluctuations of the early universe and the subsequent evolution of cosmic structures is a story that is still being written. But it is a story that is increasingly pointing towards a deep and profound unity. A unity where the smallest, most fundamental quantum processes are responsible for shaping the largest and most magnificent structures in the cosmos. The study of black holes as quantum objects is no longer a niche, theoretical pursuit. It is at the very heart of our quest to understand the universe, a quest that is revealing a cosmos that is more interconnected, more dynamic, and more wonderfully quantum than we ever imagined. In the quest to understand the universe's first fiery moments, scientists have developed a powerful and innovative new tool, the simulation of quantum states on hyperbolic lattices. This cutting-edge approach, which combines the abstract beauty of non-Euclidean geometry with the computational power of modern physics, is allowing researchers to recreate the extreme and previously inaccessible conditions of the early universe in a controlled, virtual environment. This is a groundbreaking leap forward, a way to bridge the vast gap between the theoretical predictions of quantum physics and the observational data from our telescopes. At the heart of this new approach is the use of conformal field theories, CFTs, a special and highly symmetric class of quantum field theories that are thought to describe the behavior of matter at very high energies, like those present in the immediate aftermath of the Big Bang. And the natural geometric stage for these theories is not the familiar flat space of our everyday experience, but a negatively curved, hyperbolic space. By placing these CFTs on a discrete computational lattice that has the geometry of a hyperbolic plane, physicists can now perform precise and reliable simulations of the quantum dynamics of the infant cosmos. This is a remarkable achievement, a virtual time machine that allows us to explore the physics of the universe's birth. One of the most intriguing aspects of this research is its ability to shed new light on the process of cosmic inflation. As we have seen, inflation is the theory that the universe underwent a period of hyper-accelerated expansion in its first moments. This rapid stretching of spacetime would have taken the tiny, unavoidable quantum fluctuations of the primordial vacuum and amplified them to macroscopic and even astronomical scales. These amplified fluctuations then became the seeds of all the structure we see in the universe today. The galaxies, the clusters, the vast cosmic web. The hyperbolic lattice simulations are providing a new and powerful way to study this process in detail. They allow physicists to model the complex, quantum interplay between the inflating spacetime and the fluctuating quantum fields, and to calculate the precise statistical properties of the resulting density variations. These theoretical predictions can then be compared with the exquisitely precise measurements of the temperature fluctuations in the cosmic microwave background. The remarkable agreement between the predictions of these quantum simulations and the observational data is one of the strongest pieces of evidence we have that this strange and beautiful story of our quantum origins is, in fact, correct. The search for the echoes of these primordial quantum events is not limited to simulations. It is also a major focus of observational cosmology. The stretching of spacetime during inflation is predicted to have generated not just density fluctuations, but also primordial gravitational waves, ripples in the very fabric of spacetime itself. These gravitational waves are a unique and pristine messenger from the very beginning of time. They travel to us almost completely unimpeded from the moment of their creation, carrying with them a direct and unambiguous signature of the physics of inflation. Detecting these incredibly faint, ancient ripples is one of the holy grails of modern cosmology. And the search is on. Experiments like BICEP Keck at the South Pole and the upcoming Simons Observatory in the Atacama Desert are designed to search for a specific, swirling pattern of polarization in the cosmic microwave background, a B-mode polarization pattern that can only be produced by primordial gravitational waves. A definitive detection of these B-modes would be a Nobel Prize-worthy discovery, a direct confirmation of inflation, and a window into the physics of the universe at energies far beyond the reach of any terrestrial particle accelerator. Another, equally profound, quantum phenomenon that may have played a crucial role in the early universe is entanglement. Could the particles created in the fiery aftermath of the Big Bang have been born in a state of massive, cosmic-scale entanglement? And could this primordial entanglement have influenced the subsequent evolution of the universe? This is a fascinating and active area of research. Some have speculated that the strange, large-scale correlations that we see in the cosmic microwave background, the fact that the temperature fluctuations on opposite sides of the sky seem to be correlated in ways that defy a simple causal explanation, could be a sign of this primordial entanglement. Recent laboratory experiments have shown that entangled states can be surprisingly robust, capable of surviving in the kind of hot, dense, and chaotic environments that were present in the early universe. This lends a new plausibility to the idea that entanglement is not just a feature of our present-day quantum world, but was a key player in the cosmic drama from the very beginning. It suggests a universe that was born not as a collection of separate, independent particles, but as a single, holistic, and deeply entangled quantum state. The cosmic microwave background, that faint, ancient light that fills all of space, is our most powerful and precious tool for studying the quantum nature of the early universe. The tiny, 1 part in 100,000 temperature anisotropies in the CMB are a direct snapshot of the quantum fluctuations that existed when the universe was just 380,000 years old. By analyzing the precise statistical properties of these fluctuations, their size distribution, their correlations, their subtle deviations from perfect randomness, cosmologists can test the predictions of different models of inflation and can search for the telltale signs of new, exotic physics. Recent, increasingly precise maps of the CMB from missions like the Planck satellite have revealed subtle anomalies, features in the data that are not perfectly explained by our simplest models of inflation. There is a strange cold spot, a particularly large and cold region of the sky. There is a curious alignment of the largest scale patterns of fluctuation, a cosmic axis of evil, as it has been provocatively nicknamed. While these anomalies could just be statistical flukes, the result of looking at a single realization of a random process, they have also fueled speculation that they could be the signature of something deeper, something beyond our standard cosmological model. Could the cold spot be the aforementioned bruise from a collision with another bubble universe? Could the strange alignment be a sign of a more complex, anisotropic inflationary process, or even a relic of a pre-inflationary era? These are tantalizing, if highly speculative, possibilities. And they are driving a new wave of theoretical and observational research. The universe, it seems, is still full of surprises, and its oldest light may yet hold the key to its deepest secrets. The connection between the quantum and the cosmos is also being probed in our most powerful particle accelerators, by smashing particles together at incredibly high energies. Experiments at the Large Hadron Collider are recreating, for a fleeting moment, the conditions of the early universe, a state known as a quark-gluon plasma. In this state, the protons and neutrons themselves melt, and their constituent quarks and gluons are free to move around in a hot, dense, and strongly interacting liquid. By studying the properties of this primordial plasma, physicists can learn about the nature of the strong nuclear force at the highest energies, and can test the predictions of quantum chromodynamics in an extreme regime that is otherwise inaccessible. These experiments are a form of cosmic archaeology, a way to study the fossilized remnants of the universe's first moments in a controlled, laboratory setting. The quantum mechanics of the Big Bang also brings us face to face with one of the most profound and challenging questions in all of science: what came before the Big Bang? The Standard Model, with its initial singularity, seems to suggest that this question is meaningless, but a new class of theories, rooted in a quantum description of gravity, is beginning to offer a different and perhaps more satisfying answer. Theories like loop quantum cosmology, an application of loop quantum gravity to the early universe, suggest that the Big Bang was not an absolute beginning, but a big bounce. In this scenario, our universe arose from the collapse of a previous contracting universe. As the contracting universe reached an incredibly high density, the quantum nature of space-time itself, its fundamental discreteness, would have created a powerful repulsive force, preventing the formation of a true singularity and causing the universe to bounce back into a new phase of expansion. In this picture, The universe is part of an eternal, cyclical process, with no absolute beginning or end. While we have no direct experimental evidence for this scenario yet, it is a mathematically consistent and conceptually beautiful idea. And it is an idea that could, in principle, be tested. The bounce would have left a specific and potentially detectable signature in the cosmic microwave background or in the spectrum of primordial gravitational waves. The search for these signatures is one of the most exciting and ambitious goals of future cosmological observations. The quest to understand the quantum mechanics of the early universe is a quest that is pushing the boundaries of our knowledge in every direction. It is a quest that connects the largest scales of the cosmos with the smallest, the most ancient light with the most advanced laboratory experiments, the most abstract theories with the most profound existential questions. It is a quest that is revealing a universe that was born from the subtle, beautiful, and endlessly creative dance of quantum probability. A universe whose deepest secrets are still waiting to be uncovered in the faint, ancient echoes of its own quantum beginning. The vast, dark, and seemingly empty spaces of our universe are not empty at all. They are filled with a mysterious, invisible substance, a dark matter that does not emit, absorb, or reflect light. And yet its gravitational influence is the dominant force that shapes the cosmos. It is the invisible scaffolding upon which the luminous structures of the universe, the stars, the galaxies, the great cosmic web are built. The existence of dark matter is not a speculation. It is a conclusion that is forced upon us by a wealth of independent astronomical observations. We see its effects in the rapid rotation of galaxies, where the outer stars are moving far too fast to be held in orbit by the visible matter alone. We see it in the gravitational lensing of distant light, where the gravity of massive galaxy clusters bends and distorts the images of background objects far more than their visible mass could account for. And we see it in the large-scale structure of the universe itself, the intricate, web-like pattern of filaments and voids, which our computer simulations tell us could not have formed without the gravitational influence of a vast, unseen component of matter. And yet, despite the overwhelming evidence for its existence, the nature of dark matter remains one of the greatest unsolved mysteries in all of science. We know it is there. We know it has gravity. But we have no idea what it is. This is a profound and humbling state of affairs. It means that 85% of the matter in our universe is made of a substance that is completely unknown to us. A substance that is not part of our otherwise incredibly successful standard model of particle physics. The quest to identify the dark matter particle is one of the most urgent and exciting challenges in modern science. A quest that is being pursued on multiple fronts, from the deepest underground laboratories to the most powerful particle accelerators and the most sensitive space telescopes. And it is a quest where the tools and concepts of quantum mechanics are playing an increasingly central role. One of the most promising avenues in the search for dark matter is the use of exquisitely sensitive, quantum-based detectors. The leading candidates for dark matter particles are weakly interacting massive particles. WIMPs, hypothetical particles that would have been produced in the hot, dense early universe and would interact with normal matter only through the weak nuclear force and gravity. These interactions would be incredibly rare, which is why dark matter is so difficult to detect. But they are not impossible. In deep underground laboratories, shielded from the constant bombardment of cosmic rays, physicists have built large detectors, filled with materials like liquid xenon or germanium crystals, in the hope of catching the faint, fleeting signal of a WIMP bouncing off an atomic nucleus. The challenge is immense. The expected signal is a tiny, almost imperceptible recoil of a single nucleus, an event that is easily drowned out by the background noise from natural radioactivity. This is where quantum technology comes in. A recent groundbreaking experiment at Fermilab and the University of Chicago has demonstrated a new and incredibly sensitive technique that uses the tools of quantum computing to search for a different kind of dark matter candidate, the axion. Axions are hypothetical, ultralight particles that were originally proposed to solve a different puzzle in particle physics, but which have also emerged as a compelling dark matter candidate. In the presence of a strong magnetic field, an axion could, very rarely, convert into a photon of a specific frequency. The experiment uses a superconducting qubit, the building block of a quantum computer, placed inside a cryogenically cooled microwave cavity. The qubit acts as an incredibly sensitive quantum antenna, capable of detecting the faint, single-photon signal that would be the telltale sign of an axion conversion. By carefully scanning through different frequencies, this quantum sensor can search for the elusive dark matter particle with a precision that was previously unattainable. This is a beautiful example of how the cutting-edge technologies developed for quantum computing are being repurposed to tackle some of the deepest and most fundamental questions in all of cosmology. Other related experiments, known as axion haloscopes, use large, powerful magnets and resonant cavities to try and amplify this faint action-to-photon conversion signal. And the search is also being pursued with quantum interferometers, devices that use the wave-like nature of light or matter to measure tiny disturbances with incredible precision. A passing dark matter particle could, in theory, cause a tiny, fleeting distortion in space-time, or a subtle change in the fundamental constants of nature, which could be detected as a phase shift in an interferometer. These are all incredibly challenging, and often needle in a haystack experiments. But they represent our best hope for finally, directly, detecting the dark matter particle and beginning to unravel its secrets. Another and equally important part of the dark matter puzzle is the search for its production in our most powerful particle accelerators. If dark matter is made of WIMPs or other new particles, then it should be possible to create them in the high-energy collisions at the Large Hadron Collider. The problem is that these dark matter particles, by their very nature, would be invisible to the detectors. They would not leave a track. They would not deposit any energy. So, how can we hope to see them? The answer is to look for what is not there. The signature of dark matter production at the LHC would be missing energy. When two protons collide, we can measure the energy and momentum of all the visible particles that fly out. If the total energy and momentum of these outgoing particles does not balance the initial energy and momentum of the colliding protons, it is a sign that some invisible particles have been produced and have escaped the detector unseen. This missing energy signature is a powerful tool in the search for new physics, and it has been used to search for a wide range of dark matter candidates, from the superpartners of supersymmetry to the Kaluza-Klein particles of extra-dimensional theories. So far, no definitive, unambiguous signal of dark matter production has been seen at the LHC. This has led some to question the WIMP paradigm and to explore other, more exotic possibilities. One of these is the idea of a hidden sector or a dark sector, a whole new family of particles and forces that interact very weakly, or not at all, with our familiar, standard model particles. Dark matter could be the lightest, stable particle in this hidden sector, and there could be portal interactions, new, very weak forces that connect our world with this dark world. The LHC is searching for the signs of these portals, for the rare events where a collision produces a particle, like a dark photon, that can then decay into the hidden sector. The search for dark matter is a beautiful and compelling example of the deep and powerful interplay between the very small and the very large. The fate of galaxies and the structure of the cosmos are determined by the properties of a particle that is so small, so weakly interacting, that it has, so far, completely eluded our most sensitive detectors, The quest to find it is a quest that is pushing the boundaries of our technology, of our theories, and of our very understanding of the quantum world. The mystery of dark matter is not just about identifying a new particle. It is about understanding a whole new sector of reality, a sector that may be as rich and as complex as the one we are familiar with. And the quantum nature of this dark world could have profound and unexpected implications for the cosmos. One of the most intriguing possibilities is that dark matter is not a single, simple particle, but has its own complex interactions, its own dark chemistry. Some anomalies in astronomical observations, like the surprisingly low density of dark matter in the cores of some dwarf galaxies, could be explained if dark matter particles can interact with each other through a new dark force. This self-interacting dark matter model is one that is being actively explored, both theoretically and observationally. The quantum nature of dark matter could also play a role in the formation of the very first structures in the universe. In the standard cold dark matter model, the dark matter particles are slow-moving and clumped together under gravity to form small, dense halos. These halos then act as the gravitational seeds for the formation of the first stars and galaxies. But if dark matter has different quantum properties, if it is fuzzy or wave-like, for example, then this process of structure formation could be very different. Fuzzy dark matter models, where the dark matter is made of incredibly light, bosonic particles that form a giant, galaxy-sized Bose-Einstein condensate, predict that the formation of very small, dwarf galaxies should be suppressed. A prediction that could be tested with future, ultra-deep astronomical surveys. Another, even more radical idea is that dark matter could be a window into the multiverse. In some brain world models, as we have seen, our universe is a three-dimensional membrane floating in a higher dimensional space. In this picture, dark matter could be the gravitational influence of ordinary matter that is confined to a nearby parallel brane. We cannot see the matter on the other brane, but we can feel its gravity, which leaks into our dimension. This is a beautiful and speculative idea, but it is one that makes certain testable predictions about the distribution and behavior of dark matter that could be searched for in future, high-precision astronomical observations. The quest to understand dark matter is a quest that is leading us into some of the deepest and most mysterious corners of the quantum world. It is a quest that is forcing us to be more creative, more imaginative, and more open-minded in our thinking about the fundamental nature of reality. Whether dark matter turns out to be a WIMP, an axion, a primordial black hole, or something even stranger and more unexpected, its discovery will undoubtedly trigger a revolution in our understanding of the cosmos. A revolution that will reveal a universe that is not just darker, but also far richer and more wonderfully quantum than we ever imagined. The strange, ghostly, and deeply interconnected world of quantum mechanics finds its ultimate expression in the intense, extreme, and often violent environments of the cosmos. The universe is a natural, and often spectacular, laboratory for testing the limits of our quantum theories, a place where the subtle, microscopic rules of the quantum realm are writ large on a celestial scale. The study of pulsars, the rapidly spinning, highly magnetized neutron stars that are the collapsed remnants of massive supernovae, is a prime example of this beautiful synergy between the quantum and the cosmic. And the hypothetical action particle, one of our leading candidates for dark matter, may be the key that unlocks a new and deeper understanding of these exotic quantum objects. Actions, if they exist, are predicted to have a very specific and very weak interaction with photons in the presence of a strong magnetic field. The incredibly intense magnetic fields of a pulsar, which can be 1 trillion times stronger than the Earth's, provide the perfect environment for this interaction to occur. A cloud of actions accumulating in the magnetosphere of a pulsar could be converted into a cloud of radiophotons, producing a specific, narrow, and potentially detectable line in the pulsar's radio spectrum. The search for this action line is a new and exciting frontier in radio astronomy, a way to use the universe's own natural particle accelerators to search for one of its most elusive and mysterious components. But pulsars are not just potential action detectors, they are, in their very essence, quantum objects. A neutron star is a star that has collapsed to such an incredible density that its atoms have been crushed out of existence. It is a giant, city-sized atomic nucleus, composed mostly of neutrons, packed together so tightly that their behavior is governed not by classical physics, but by the strange and beautiful rules of the quantum world. One of the most remarkable of these is the phenomenon of superfluidity at the incredibly high densities and relatively low temperatures inside a neutron star. The neutrons are predicted to form a superfluid, a quantum state of matter that flows with absolutely no viscosity, no friction. And the protons within the star are predicted to form a superconductor, a state that conducts electricity with zero resistance. This is not just a theoretical curiosity. The existence of this quantum superfluid in the interior of neutron stars is thought to be the explanation for one of their most mysterious and long-observed behaviors. Glitches. A pulsar, because it is constantly radiating away energy, should be spinning down at a slow, steady, and predictable rate. But occasionally, astronomers observe a sudden, abrupt increase in a pulsar's spin rate, a glitch. The leading explanation for these glitches is that they are a result of the interaction between the solid outer crust of the neutron star and the rapidly spinning superfluid interior. The superfluid, because it has no viscosity, can spin at a different rate from the crust. But occasionally, the two can become momentarily coupled, transferring a burst of angular momentum from the superfluid to the crust and causing the star to suddenly spin up. The study of these pulsar glitches is a remarkable and powerful way to probe the strange, quantum state of matter that exists in the heart of a neutron star, a state that is impossible to replicate in any terrestrial laboratory. The universe as a laboratory for quantum mechanics is a theme that extends far beyond the realm of pulsars and axions. The distant, brilliant beacons of quasars, the intensely luminous centers of young, active galaxies, powered by supermassive black holes, have recently been used to perform one of the most profound and beautiful tests of the fundamental principles of quantum mechanics itself. As we have seen, the phenomenon of quantum entanglement, the spooky action at a distance, is one of the most bizarre and counterintuitive predictions of the theory. The Bell test experiments, which have confirmed this non-local connection with incredible precision, rely on a source of true, unpredictable randomness to set the measurement directions for the two entangled particles. This is to close a potential loophole, the freedom of choice loophole, which posits that the particles and the measurement devices could have been secretly correlated in the past by some unknown, local hidden variable. To close this loophole as definitively as possible, a recent groundbreaking experiment used the light from two very distant quasars located on opposite sides of the sky to set the measurement choices. The light from these quasars has been traveling for billions of years, and it was created in two completely causally disconnected regions of the early universe. The random fluctuations in the color of this ancient light were used to trigger the measurement settings in the experiment, ensuring that there was no possible way for the entangled particles to have known in advance what they were going to be asked. The experiment, once again, confirmed the predictions of quantum mechanics with stunning accuracy, ruling out any possibility of a local, realistic explanation for entanglement. It is a beautiful and profound demonstration of how the vastness of the cosmos can be used as a tool to probe the deepest secrets of the quantum world. and how the light from the universe's dawn can be used to confirm the strange and wonderful nature of our present reality. The deep and intimate connection between the quantum world and the cosmos is a two-way street, just as the universe can be used as a laboratory to test the principles of quantum mechanics. Quantum mechanics can be used as a tool to understand the origin and evolution of the universe itself. The phenomenon of quantum tunneling, the ability of a particle to pass through a classically forbidden energy barrier, is a prime example of this synergy. As we have seen, quantum tunneling is the engine that powers the stars. The protons in the sun's core do not have enough thermal energy to overcome their mutual electrostatic repulsion and fuse together. It is only by tunneling through this repulsive barrier that they can get close enough for the strong nuclear force to take over, initiating the process of thermonuclear fusion and releasing the energy that makes life on Earth possible. But the role of quantum tunneling extends far beyond the hearts of stars. A recent groundbreaking experiment, led by the researcher Robert Wild, has shown that quantum tunneling can also play a crucial role in the cold, sparse environment of interstellar space. By simulating the conditions of these vast molecular clouds in the laboratory, the team was able to show that quantum tunneling can enable chemical reactions to occur at temperatures near absolute zero. Reactions that would be completely impossible according to classical chemistry. This is a profound discovery. It means that the complex organic molecules that are the building blocks of life may not just be formed in the warm, gentle environments of protoplanetary disks, but can also be synthesized in the coldest, darkest, and emptiest regions of the galaxy through the strange and wonderful magic of quantum tunneling. It suggests that the chemical precursors to life are far more widespread and are formed far more readily than we ever thought possible. From the fiery hearts of stars to the cold depths of interstellar space, the subtle and often counterintuitive rules of the quantum world are the silent, invisible architects that are shaping the cosmos, creating the conditions for complexity, for chemistry, and ultimately, for life itself. The universe, it seems, is a quantum phenomenon, through and through. The cosmic story of creation, from the first fiery moments of the Big Bang to the emergence of the rich and complex universe we see today, is a story that is fundamentally shaped by the principles of quantum mechanics, the very existence of matter, the stability of atoms, the light of the stars. All of these are a testament to the strange and beautiful rules that govern the subatomic world. And as our understanding of these quantum processes deepens, we are beginning to piece together a new and more profound picture of our own cosmic origins. The phenomenon of quantum tunneling, as we have seen, is not just a laboratory curiosity. It is a fundamental engine of cosmic evolution. It is what allows stars to shine, releasing the energy that powers life and forging the heavy elements that make up our bodies and our world. And it is a process that may be at work in the most extreme and mysterious environments in the universe. The intense gravitational fields near a black hole, for example, create a powerful energy barrier for particles trying to escape. But quantum tunneling could, in theory, allow particles to leak out, a process that is related to, but distinct from, Hawking radiation. This could have profound implications for our understanding of black hole thermodynamics and the ultimate fate of the information that falls into them. Similarly, the study of the dense, exotic matter in the heart of a neutron star is a study of quantum mechanics in its most extreme form. The immense pressure crushes matter into a state where quantum effects, like the Pauli exclusion principle and superfluidity, become the dominant reality. Our observations of these strange quantum stars, through their regular clock-like pulses and their occasional sudden glitches, are providing a unique and powerful window into the behavior of matter at densities that are impossible to replicate on Earth. And what of the very beginning? The moment of the Big Bang itself is the ultimate quantum event, a moment where the entire universe was compressed into a state of unimaginable energy and density, a state where the laws of classical physics break down completely. To understand this moment, we need a theory of quantum gravity, a theory that can describe the quantum nature of space-time itself. And while we do not yet have a complete theory, the clues are beginning to emerge. The study of the cosmic microwave background, the faint afterglow of the Big Bang, has revealed a pattern of tiny, primordial fluctuations that are the fossilized remnants of the quantum fluctuations of the early universe. These fluctuations stretch to astronomical scales by the process of cosmic inflation, are the seeds from which all the galaxies and large-scale structures in the universe grew. We are, in the most literal sense, the macroscopic manifestation of microscopic quantum randomness. The journey to understand the quantum cosmos is a journey that is still in its infancy. But it is a journey that is already revealing a universe that is far stranger, more interconnected, and more wonderfully creative than our classical intuition could ever have imagined. The discoveries of tunneling, of fusion, of superfluidity, of primordial fluctuations are all just stepping stones on a path towards a deeper and more unified understanding of reality. And as our tools, both theoretical and experimental, become more powerful, we are poised to uncover even more profound and beautiful secrets. Future observations of primordial gravitational waves could give us a direct glimpse into the physics of inflation. The moment when the quantum became the cosmic, the direct detection of Hawking radiation from a black hole would be a stunning confirmation of the deep connection between gravity, thermodynamics, and the quantum vacuum. And the development of a complete theory of quantum gravity would be the ultimate triumph of the human intellect. A single, elegant theory that could describe the entire universe, from the smallest quantum fluctuation to the largest cosmic structure, within a single, coherent framework. But this quest is not just about finding answers. It is also about asking better questions. How does the strange, non-local nature of quantum entanglement play out on a cosmic scale? What is the role of the observer, of consciousness? In a universe that seems to be fundamentally probabilistic, is our universe just one of many in a vast quantum multiverse? These are questions that may not have simple answers, questions that may push the very limits of what science is capable of addressing. But they are questions that we are now, for the first time in human history, equipped to ask in a rigorous, scientific way. The study of the quantum cosmos is not just about understanding the universe out there, it is also about understanding ourselves. We are quantum beings, living in a quantum universe. The atoms that make up our bodies, the light that allows us to see, the very thoughts that flicker through our minds, all of these are governed by the same strange and beautiful rules of the quantum world. To study the quantum cosmos is to study the very fabric of our own existence. And as we continue on this journey, as we peer deeper into the mysteries of the quantum realm, we are not just unraveling the secrets of the universe, we are also, in a very real sense, unraveling the secrets of ourselves. The accelerating expansion of the universe, driven by the mysterious force of dark energy, is one of the most profound and challenging discoveries in the history of science. And the quantum world, with its seething, energetic vacuum, may hold the key to understanding this cosmic mystery. The incessant, jittery fluctuations of the quantum fields that permeate all of space give rise to a zero-point energy, an irreducible minimum energy of the void, and this vacuum energy, according to our current understanding, should have a powerful gravitational effect. It should act as a cosmological constant, a form of energy with a strong negative pressure that would cause the very fabric of spacetime to expand at an accelerating rate. This is a beautiful and elegant connection. It suggests that the grand cosmic drama of the universe's expansion is being driven by the subtle, microscopic dance of quantum mechanics. But this beautiful picture is marred by the vacuum catastrophe, the colossal discrepancy between the theoretical calculation of the vacuum energy and its observed value. This has led many physicists to explore alternative possibilities. Perhaps dark energy is not the energy of the vacuum, but is a new, dynamic quantum field, a quintessence that is slowly evolving over cosmic time. Or perhaps our understanding of gravity itself is incomplete, and the accelerated expansion is a sign of new physics beyond Einstein's general relativity. But another, even more profound, possibility has emerged from these investigations: the quantum fluctuations of the early universe, the very same fluctuations that are thought to have seeded the formation of galaxies, may have also played a direct role in shaping the properties of dark energy itself. Some theories suggest that the value of the cosmological constant is not a fixed, fundamental parameter of nature, but is a dynamical variable, a value that was set by the specific, random outcome of quantum fluctuations during the inflationary epoch. In this view, our universe is just one of a vast cosmic multiverse of possibilities, and we just happen to live in a universe where the quantum dice roll of inflation resulted in a small, positive value for the dark energy, a value that is conducive to the formation of structure and life. This is a deeply unsettling, but also deeply compelling idea. It suggests that the ultimate fate of our universe, its destiny to expand forever into a cold, dark, and empty void, may be the result of a single, random quantum event that occurred in the first fraction of a second of its existence. The study of the early universe, through the lens of quantum mechanics, is a journey into the very heart of creation. It is a quest to understand how, from a state of almost perfect simplicity and uniformity, the rich, complex, and beautiful tapestry of the cosmos was woven. The inflationary period, that brief, but spectacular, moment of hyper-accelerated expansion, is the key to this story. It is the bridge between the quantum and the cosmic, the mechanism that took the microscopic, probabilistic weirdness of the quantum world and stretched it to astronomical scales. The density variations that gave rise to galaxies, the primordial gravitational waves that may one day tell us about the physics of the very beginning, the very properties of the dark energy that is shaping our future. All of these may be the fossilized relics of the quantum fluctuations of the inflationary vacuum. The cosmic microwave background is our most precious and powerful window into this primordial quantum era. The tiny 1 part in 100,000 temperature fluctuations in the CMB are a direct photographic image of the state of the universe when it was just a few 100,000 years old. And by studying the precise statistical properties of these fluctuations, we can test the predictions of our quantum cosmological models with incredible precision. And these tests have been, so far, stunningly successful. The observed pattern of fluctuations is a near-perfect match for the predictions of the simplest models of inflation, a powerful confirmation of the idea that the grand architecture of our cosmos has its roots in the inherent and beautiful uncertainty of the quantum world. But the study of the CMB is also revealing subtle hints of new and even stranger physics. The anomalies we have discussed, the cold spot, the cosmic axis of evil, may be statistical flukes, but they may also be the first faint whispers of a reality that is even more complex and more wonderfully quantum than we have yet imagined. They may be the signs of a more complex inflationary history, of a pre-inflationary era, or even of a connection to a larger cosmic multiverse. The universe, it seems, is still full of quantum secrets, and its oldest light is our best hope for uncovering them. The connection between the quantum and the cosmic is not just about the early universe. It is also about the here and now. The strange, non-local reality of quantum entanglement, the spooky action at a distance, is a phenomenon that is now being tested on a cosmic scale. As we have seen, the use of distant quasars to set the measurement choices in a Bell test experiment has provided our most definitive refutation yet of Einstein's local realism. It is a beautiful demonstration of how the vastness of the cosmos can be used as a tool to probe the deepest and most counterintuitive aspects of the quantum world. But what if this connection goes even deeper? What if the universe itself, at the very largest scales, is a single, vast, and deeply entangled quantum system? This is a mind-bending idea, but it is one that is being taken seriously by some of the most creative thinkers in modern physics. The strange, large-scale correlations that we see in the cosmic microwave background, the fact that the temperature fluctuations on opposite sides of the sky seem to be more correlated than they should be, could be a sign of a primordial, cosmic-scale entanglement, a non-local connection that was established in the very first moments of the universe's existence and has persisted to this day. If this is true, it would mean that our universe is not a collection of separate, causally disconnected regions, but is a single, holistic, and deeply non-local quantum entity. It would be the ultimate confirmation of the quantum worldview, a vision of a universe that is profoundly and beautifully. 1. The study of top quarks and other heavy, unstable particles at the Large Hadron Collider is also providing a new and powerful window into the interplay between the quantum world and the extreme environments of the cosmos. The discovery that entanglement can persist, even for a fleeting moment, in these high-energy, chaotic collisions is a testament to the robustness of this strange quantum connection, and it is providing crucial insights into the physics of the early universe, of black holes, of the exotic states of matter that may exist in the hearts of neutron stars. By recreating these extreme cosmic conditions in the laboratory, we are learning about the fundamental quantum rules that govern the universe in its most violent and most mysterious regimes. The journey to understand the quantum cosmos is a journey that is still very much in progress, but it is a journey that has already transformed our understanding of the universe and our place within it. It has shown us a universe that is born from the creative uncertainty of the quantum void, a universe whose grandest structures are the macroscopic fossils of microscopic quantum fluctuations, a universe that is bound together by the invisible, instantaneous threads of quantum entanglement. And it has revealed a deep and profound unity between the very small and the very large, between the laws that govern the subatomic world and the laws that shape the destiny of the cosmos itself. The next generation of experiments, the more precise maps of the cosmic microwave background, the more sensitive gravitational wave detectors, the more powerful particle accelerators will undoubtedly reveal even more profound and beautiful secrets. They may confirm the existence of primordial gravitational waves, providing a direct glimpse into the moment of inflation. They may unravel the mystery of dark matter, revealing a whole new, hidden sector of the quantum world. They may even provide the first tantalizing hints of a final, unified theory of quantum gravity. But whatever these future discoveries may be, one thing is certain: they will only deepen our appreciation for the strange, beautiful, and endlessly fascinating quantum nature of our cosmic home. They will remind us, once again, that the universe is not just stranger than we imagine, but stranger than we can imagine. The quest to understand the universe, in all its vastness and complexity, is a journey that inevitably leads us to the most extreme, the most exotic, and the most mysterious objects in the cosmos. And at the very heart of this journey lies the study of black holes and neutron stars. The ultra-dense, collapsed remnants of massive stars, celestial objects that are not just laboratories for extreme physics, but are, in their very essence, Macroscopic. Quantum phenomena. The recent groundbreaking experiment that used hyperbolic lattices to simulate the quantum states of the early universe is a powerful example of this new and exciting frontier. By creating an artificial computational spacetime with the geometry of a hyperbolic plane, physicists are now able to model the behavior of quantum fields in the kind of curved, dynamic environments that are thought to have existed in the immediate aftermath of the Big Bang, or in the immediate vicinity of a black hole. This is a revolutionary new tool. It allows us to explore the complex and often counterintuitive interplay between quantum mechanics and general relativity in a controlled, virtual environment, providing new insights into some of the deepest and most long-standing puzzles in all of science. One of these puzzles is the nature of the strong nuclear force at the highest energies. The theory of quantum chromodynamics QCD describes this force with incredible precision, but its equations become incredibly difficult to solve in the extreme. High-density environments of a neutron star core or a quark-gluon plasma. The hyperbolic lattice simulations are providing a new and powerful way to tackle these calculations, shedding new light on the exotic states of matter that are thought to exist in these extreme cosmic crucibles. The core of a neutron star, for example, is a place of almost unimaginable density, a place where matter is crushed to a state that is billions of times denser than anything we can create on Earth. In this environment, the neutrons themselves are predicted to dissolve into a sea of their constituent quarks and gluons, a state of matter known as quark matter. And the quarks themselves may form a color superconductor, a strange quantum state where they flow with zero resistance. The study of these exotic states of matter is not just a theoretical exercise. It has real, observable consequences. The precise properties of the matter in a neutron star's core determine its maximum mass, its cooling rate, and its behavior during the violent merger with another neutron star. The gravitational waves and the electromagnetic signals that we detect from these mergers are a direct probe of the quantum physics of extreme density, a way to test our theories of QCD and exotic matter in a way that is impossible in any terrestrial laboratory. The quantum nature of these extreme astrophysical objects is not just about the state of their matter, it is also about the very fabric of space-time itself. The black hole information paradox, as we have seen, is a deep and profound conflict between the principles of quantum mechanics and general relativity, and its resolution is thought to lie in a deeper quantum understanding of the black hole's event horizon. The hyperbolic lattice simulations and other related theoretical tools are allowing physicists to explore the quantum geometry of the event horizon in unprecedented detail. They are studying how quantum information is scrambled and encoded on the horizon, and how it might be subtly imprinted on the outgoing Hawking radiation. This is a quest that is leading to some of the most radical and revolutionary ideas in modern physics, including the Ehrlich conjecture and the holographic principle, ideas that suggest that space-time itself may be an emergent quantum informational phenomenon. The study of Bose-Einstein condensates, BECs, another exotic quantum state of matter, is also providing a powerful new window into these mysteries. A BECE is a state where a large number of bosonic particles cooled to temperatures near absolute zero all collapse into the same single quantum state, behaving as a single, coherent, macroscopic quantum object. These systems are a kind of quantum simulator, a controllable laboratory system that can be used to model the behavior of other, more complex and inaccessible quantum systems. A recent experiment conducted aboard the International Space Station has created the coldest and most stable BECCs ever produced. And in the microgravity environment of space, these quantum clouds can be studied for much longer periods of time, allowing for incredibly precise measurements of their quantum properties. Scientists are now using these space-based BECs to simulate a wide range of astrophysical and cosmological phenomena, from the dynamics of dark energy to the quantum nature of black holes. One of the most exciting possibilities is the creation of a graviton condensate. Gravitons, the hypothetical quantum particles of gravity, are bosons, and so, in principle, they could form a Bose-Einstein condensate. Some have speculated that a black hole could be, in its very essence, a condensate of a vast number of gravitons, a single, macroscopic quantum object held together by its own collective gravity. While this is a highly speculative idea, the ability to study the properties of BECs in the laboratory, and now in space, is providing a new and powerful set of tools for exploring these profound and beautiful ideas. The quantum world, it seems, is everywhere. It is in the fiery hearts of stars, in the cold depths of interstellar space, in the dense, exotic matter of neutron stars, and in the enigmatic, information-scrambling horizons of black holes. And the study of these cosmic quantum laboratories is revealing a universe that is far more interconnected, more dynamic, and more wonderfully strange than we ever imagined. The phenomenon of superfluidity, the ability of a quantum fluid to flow with zero viscosity, is another beautiful example of this cosmic quantum connection. We have already seen how the superfluidity of neutrons is thought to be responsible for the glitches in the rotation of pulsars. But superfluidity may also play a role in the very formation of these objects. The collapse of a massive star in a supernova explosion is an incredibly complex and violent event. And recent sophisticated computer simulations have shown that the superfluid nature of the nascent neutron star's core could have a dramatic effect on the dynamics of the explosion itself, influencing the way that neutrinos are trapped and released, and potentially playing a key role in powering the explosion. The study of neutrinos themselves, the ghostly, weakly interacting particles that are produced in vast numbers in the Sun and in supernovae, is another frontier where the quantum and the cosmic meet. The discovery that neutrinos have a tiny but non-zero mass, and that they can oscillate or transform from one flavor to another as they travel, was a major breakthrough in particle physics and a clear sign of physics beyond our standard model. And the universe itself is our most powerful neutrino detector. The IceCube Neutrino Observatory at the South Pole uses a cubic kilometer of the Antarctic ice as a giant natural detector, searching for the faint flashes of light produced when a high-energy neutrino from a distant astrophysical source interacts with an atom in the ice. These high-energy neutrinos are a unique and powerful messenger, a way to probe the most violent and energetic process in the universe. From the hearts of active galactic nuclei to the mysterious sources of ultra-high-energy cosmic rays. And their quantum properties, their oscillations and their interactions, are a key part of the story. The quantum world is not a separate, isolated realm of reality. It is the fundamental, underlying operating system of the entire cosmos. And as our ability to observe the universe and to simulate it becomes more and more sophisticated, we are beginning to see the deep and beautiful ways in which the subtle, strange, and often counterintuitive rules of the quantum realm are responsible for shaping the grand, magnificent, and awe-inspiring tapestry of the cosmos we inhabit. The journey to understand the quantum cosmos is a journey that is constantly pushing the boundaries of our technology and our imagination. And in the year 2024, a series of groundbreaking discoveries have brought the strange and beautiful world of quantum mechanics into sharper focus than ever before, revealing its profound influence on everything from the heaviest particles in the universe to the most extreme and exotic celestial objects. One of the most remarkable of these was the first definitive observation of quantum entanglement in top quarks, the most massive elementary particles ever discovered. This was an achievement of incredible technical virtuosity, conducted by the CMS collaboration at the Large Hadron Collider. Top quarks are incredibly unstable, decaying in a fraction of a yoctosecond, a time so short it is difficult to comprehend. The fact that the delicate, non-local connection of entanglement can be established and maintained, even for this fleeting instant, in the chaotic, high-energy environment of a proton-proton collision, is a stunning testament to the robustness of this fundamental quantum phenomenon. It pushes the verification of quantum mechanics into a new and previously unexplored regime of mass and energy, a regime that is closer to the conditions of the early universe than any we have been able to study before. This discovery is not just a confirmation of what we already knew. It opens up a new window into the quantum world. The top quark, because of its enormous mass, has a unique and very strong coupling to the Higgs field. By studying the entanglement of top quarks, physicists can probe the quantum nature of the Higgs field itself and can search for subtle deviations from the predictions of the standard model that could be a sign of new physics, of new particles or new forces that interact preferentially with the heaviest particles. Another, related breakthrough came from the study of entanglement in mesons, composite particles made of a quark and an antiquark. By studying the entangled decay products of these particles, physicists are gaining new insights into the subtle and still not fully understood violation of CP symmetry, the slight difference in the behavior of matter and antimatter that is thought to be responsible for the fact that our universe is made of matter at all. The ability to create and manipulate these entangled, heavy particle states is not just about testing fundamental physics. It is also about developing new quantum technologies. While photons are the current workhorse of quantum communication, heavy particles could, in principle, offer new and more robust ways to encode and transmit quantum information in certain specific contexts. The year 2024 has also been a landmark year for the study of exotic quantum states of matter on a cosmic scale. The observation of Bose-Einstein condensates aboard the International Space Station has provided a new and powerful laboratory for studying the collective quantum behavior of matter in a microgravity environment. These experiments are not just about creating a new fifth state of matter. They are about using these highly controllable, macroscopic quantum objects to simulate other, more complex and inaccessible systems, from the superfluid core of a neutron star to the quantum nature of dark energy. This is the dawn of the era of quantum simulation, a new and powerful tool for exploring the universe. The study of neutron stars themselves has also seen remarkable progress. The detection of gravitational waves from the merger of two neutron stars has provided an unprecedented multi-messenger view of these extreme quantum objects. By combining the gravitational wave signal with the electromagnetic signals, the light, the gamma rays, the radio waves that are emitted in the aftermath of the collision, astronomers are able to piece together a detailed picture of what happens when two of these city-sized atomic nuclei smash into each other. This data is providing crucial, new constraints on the equation of state of nuclear matter, the relationship between the pressure and the density of matter at the most extreme conditions in the universe. It is helping us to understand whether the core of a neutron star is made of simple neutrons or of more exotic states, like a quark-gluon plasma or strange matter. These are questions that are at the very heart of nuclear and particle physics. And the universe itself is providing us with the ultimate laboratory for answering them. The connection between the quantum and the cosmic is also being explored in the search for dark matter. As we have seen, the use of quantum sensors, like superconducting qubits and interferometers, is revolutionizing the search for actions and other light-dark matter candidates. These experiments are a beautiful example of how the tools of one quantum revolution, the revolution in our ability to control and manipulate single quantum systems, are being used to fuel the next, the revolution in our understanding of the fundamental nature of the cosmos. The year's discoveries are a powerful reminder that the universe is a deeply quantum place. The strange and beautiful rules of the quantum world are not confined to the sterile, controlled environment of the laboratory. They are at work everywhere, from the fleeting, entangled dance of top quarks at the LHC to the superfluid heart of a distant neutron star. From the quantum foam of the early universe to the very fabric of space-time itself. And as our ability to observe, to simulate, and to understand these quantum phenomena continues to grow, we are not just adding new details to our picture of the universe. We are fundamentally transforming it, revealing a cosmos that is more interconnected, more dynamic, and more wonderfully, beautifully, and profoundly quantum than we ever imagined. The study of quantum spin, an intrinsic and deeply mysterious property of fundamental particles, has also seen a year of remarkable and illuminating discoveries, further blurring the line between the microscopic world of the quantum and the macroscopic world of the cosmos. Quantum spin is not a physical rotation in the classical sense. It is a fundamental quantum mechanical property, a form of intrinsic angular momentum that gives particles a kind of magnetic orientation. And the alignment and interaction of these tiny quantum spins can have profound and large-scale consequences. A recent groundbreaking observation has revealed peculiar and highly ordered spin alignments in the expanding remnants of a supernova explosion. This suggests that the violent, chaotic process of a star's death may be influenced, and perhaps even shaped, by the collective quantum behavior of the spins of its constituent particles. The core collapse of a massive star is an event of almost unimaginable complexity. As the star's core is crushed by gravity to the density of an atomic nucleus, the spins of the neutrons and protons play a crucial role. The Pauli exclusion principle, which forbids two identical fermions from occupying the same quantum state, creates a powerful degeneracy pressure that resists the collapse. And the alignment of the spins of the particles can give rise to a powerful macroscopic magnetic field. The discovery of these spin-aligned structures in a supernova remnant provides a new and powerful piece of evidence for the importance of these quantum effects in the dynamics of stellar explosions. It suggests that the shape and evolution of a supernova remnant may not just be determined by hydrodynamics and shock waves, but also by the subtle and previously unobservable quantum magnetism of the exploding star. This has a direct bearing on our understanding of neutron stars. The incredibly strong magnetic fields of pulsars and magnetars are one of their most defining and also most mysterious features. And the leading theory is that these fields are a relic of the spin-aligned quantum state of the matter in the progenitor star's core, a field that has been amplified to an incredible degree during the gravitational collapse. The new observations of spin alignment in supernova remnants provide a direct causal link in this story, connecting the quantum properties of the star before its death to the macroscopic astrophysical properties of the compact object it leaves behind. The role of quantum spin is not just limited to the death of stars, it is also a key player in their life. The magnetic fields of stars like our Sun, which are responsible for phenomena like solar flares and coronal mass ejections, are generated by a complex dynamo process in their interiors, a process that is driven by the interplay of convection, rotation, and the magnetic properties of the plasma. And at a fundamental level, these magnetic properties are determined by the quantum spin of the electrons and the atomic nuclei. By studying the polarization of the light from distant stars, a technique that is sensitive to the presence of magnetic fields, astronomers are now able to map the magnetic activity of other suns, providing new insights into the quantum dynamo processes that are at work in the hearts of stars. This is crucial for our understanding of space weather and the potential habitability of exoplanets. A planet orbiting a star with a very active and spin-driven magnetic cycle would be subject to a much more intense and variable flux of high-energy particles and radiation, which could have a profound impact on its atmosphere and its ability to support life. And what of dark matter? The nature of this mysterious, invisible substance is one of the greatest unsolved puzzles in all of science. But what if the key to its identity lies in its quantum spin? The different dark matter candidates that have been proposed, WIMPs, axions, sterile neutrinos, all have different and specific spin properties. A WIMP is predicted to be a fermion with spin 1/2. An axion is a boson with spin 0. By designing experiments that are sensitive to the spin-dependent interactions of dark matter with normal matter, physicists are hoping to finally distinguish between these different possibilities. The search for dark matter is not just a search for a new particle, it is a search for a new kind of quantum spin, a new fundamental player in the cosmic spin dance. The influence of quantum spin may even extend to the very largest scales of the cosmos. In the very early universe, the primordial plasma of particles and antiparticles would have been a sea of quantum spins, and some have speculated that a primordial cosmic magnetic field could have created a slight overall alignment of these spins, a cosmic spin polarization. While this is a highly speculative idea, such a primordial spin alignment could have left a subtle and potentially detectable signature in the cosmic microwave background, or in the large-scale distribution of galaxies. The search for these faint cosmic scale signatures of quantum spin is a new and exciting frontier in observational cosmology. The study of quantum spin is a beautiful example of the profound and often surprising interconnectedness of the universe. A single, intrinsic, and deeply quantum property of a fundamental particle can have consequences that ripple outwards, shaping the life and death of stars, the habitability of planets, the nature of dark matter, and perhaps even the large-scale structure of the cosmos itself. It is a reminder that to understand the universe, we cannot just study its different parts in isolation. We must study it as a single, unified, and deeply interconnected quantum system. And as our ability to measure and to model the subtle effects of quantum science continues to improve, we are not just adding a new chapter to our physics textbooks. We are gaining a new and more profound appreciation for the intricate, beautiful, and spin-driven music of the cosmos. The universe is constantly bombarding us with messengers from the most extreme and violent corners of the cosmos. Ultra-high energy cosmic rays, particles that have been accelerated to energies far beyond anything we can achieve on Earth, are a powerful and enigmatic probe of the fundamental laws of nature and recent discoveries. From observatories like the Pierre Auger Observatory in Argentina and the Ice Cube Neutrino Observatory at the South Pole are revealing the deep and profound role that quantum mechanics plays in the story of these cosmic travelers. These cosmic rays are not just fast, they are relics of some of the most powerful and energetic astrophysical engines in the universe. The swirling, chaotic environments around supermassive black holes, the rapidly spinning, highly magnetized magnetospheres of pulsars, the expanding, turbulent shock waves of supernova remnants. The precise mechanisms by which particles are accelerated to these incredible, ultra-high energies are still not fully understood, but it is clear that quantum processes must be at play. In the intense magnetic fields of a pulsar, for example, quantum electrodynamic effects, like the creation of electron-positron pairs from the vacuum, are thought to play a crucial role in the acceleration process. In the relativistic jets that are launched from the vicinity of a black hole, quantum tunneling may allow particles to surf the shock waves, gaining energy with each pass. The study of these cosmic accelerators is a study of quantum mechanics in its most extreme and most violent form. As these cosmic rays travel across vast, intergalactic distances to reach us, they interact with the quantum fields that fill all of space. Their journey is not a simple, straight-line path through an empty void. They interact with the photons of the cosmic microwave background, with the faint, diffuse magnetic fields that thread the cosmic web, and with the virtual particles of the quantum vacuum itself. And these quantum interactions leave a subtle but detectable imprint on the properties of the cosmic rays that we observe here on Earth. The analysis of the arrival directions of the highest energy cosmic rays, for example, has revealed a slight anisotropy, a preference for certain directions in the sky, which can only be explained by the deflection of the particles by the weak, but large-scale intergalactic magnetic fields. By modeling these interactions, and by combining the cosmic ray data with observations of high-energy neutrinos and gamma rays, we can begin to piece together a multi-messenger picture of the high-energy universe. A picture where the quantum interactions of these cosmic messengers are a key part of the story. The detection of high-energy neutrinos that are spatially correlated with potential cosmic ray sources. Like the Blazer TXS 0506+056 has been a major breakthrough in this field. Neutrinos, because they are so weakly interacting, can travel in a straight line from their source to us, acting as a perfect, undeflected pointer. The combination of the neutrino signal with the cosmic ray and gamma ray signal from the same source allows us to build a much more complete and robust picture of the underlying astrophysical engine and the quantum properties of the neutrinos themselves. Their ability to oscillate from one flavor to another as they travel is a crucial part of this picture. By studying the flavor ratio of the neutrinos that arrive at Earth, we can learn about the distance to their source and the properties of the medium they have traveled through. The composition of the cosmic rays themselves also holds important clues about their quantum origins. By studying the air showers, the vast cascades of secondary particles that are produced when a high-energy cosmic ray hits the Earth's atmosphere, we can infer the mass and energy of the primary particle. And the data from these experiments suggests that the highest energy cosmic rays are not just protons, but are a mix of heavier atomic nuclei. The study of the interactions of these heavy nuclei at very high energies in experiments at the Large Hadron Collider is providing crucial new data that can be used to model the air showers and to better understand the physics of these cosmic ray interactions. This is a beautiful example of the synergy between accelerator physics and astrophysics, between the study of the very small and the very large. The study of ultra-high-energy cosmic rays is also a powerful probe of fundamental physics itself. These particles have energies that are millions of times higher than anything we can produce in our terrestrial accelerators, making them a unique window into the behavior of matter and the laws of physics at the very highest energy scales. They can be used to test the limits of Einstein's special theory of relativity, to search for tiny energy-dependent variations in the speed of light that are predicted by some theories of quantum gravity. They can be used to search for the signs of new, exotic particles or interactions, for the decay products of super-heavy dark matter, or for the signatures of topological defects like cosmic strings. The study of these cosmic messengers is a journey to the very frontier of our knowledge. A journey that is revealing a universe that is not just full of spectacular, high-energy events, but is also governed by the subtle, beautiful, and deeply quantum rules of the subatomic world. The quantum world, it seems, is not just a strange and distant realm of subatomic particles. It is the very foundation of our cosmic home. Its principles and its paradoxes writ large on the canvas of the cosmos. The journey to understand the universe is, in the end, a journey to understand its deep and often hidden quantum nature. The groundbreaking observation of entanglement between top quarks at the LHC is a powerful testament to this. It shows us that the strange, non-local connections of the quantum world are not just a feature of light, low-energy systems, but are a robust and fundamental aspect of reality, present even in the most massive and fleeting of particles, in the most violent and chaotic of environments. This discovery is more than just a confirmation of quantum mechanics in a new regime. It is a new tool, a new window into the quantum heart of the Standard Model. By studying the entangled states of these heavy particles, we are gaining a new and more profound understanding of the Higgs field, of the nature of mass, and of the subtle asymmetries that distinguish matter from antimatter. The study of the exotic quantum states of matter in the hearts of neutron stars is another equally powerful frontier. The observation of phenomena like superfluidity and color superconductivity in these extreme astrophysical laboratories is not just a confirmation of our theories of nuclear and particle physics. It is a glimpse into a whole new realm of emergent, collective quantum behavior. A realm where the familiar rules of our terrestrial world no longer apply. These quantum stars are not just dead, collapsed objects. They are dynamic, vibrant, and deeply quantum systems whose behavior is teaching us new and profound lessons about the nature of matter itself. And the quest to understand the universe's own quantum origins through the study of the cosmic microwave background, of primordial gravitational waves, and of the physics of inflation is perhaps the grandest of all these endeavors. It is a quest that is taking us back to the very first moments of creation, to a time when the entire universe was a single, hot, dense, and deeply quantum entity. The discovery that the vast cosmic structures we see today are the macroscopic fossils of microscopic quantum fluctuations is one of the most profound and beautiful insights in the history of science. It tells us that we are, in the most literal and profound sense, children of the quantum void. The journey to understand the quantum cosmos is a journey that is full of both immense challenges and breathtaking possibilities. It is a journey that is forcing us to abandon our classical intuitions, to embrace paradox, and to develop new and more powerful ways of thinking about the world. But it is a journey that is also, in its own strange way, deeply reassuring. It is revealing a universe that is not a collection of separate, disconnected parts, but a single, vast, and deeply interconnected quantum whole. A universe where the fate of a single particle can be instantaneously linked to another across the galaxy, where the quantum jiggle of the vacuum can seed the formation of 1 trillion stars, where the microscopic rules of the subatomic world can shape the ultimate destiny of the entire cosmos. And as we continue on this journey, as we peer deeper into the quantum heart of reality, we are not just unraveling the secrets of the universe, we are also, in a very real sense, discovering our own deep and undeniable connection to the strange, beautiful, and wonderfully quantum cosmos that has given us birth.